Okay, good morning, everybody. We can start today's session, and it's a pleasure to introduce Professor LeBrun for his second lecture on the geometry of four manifolds, curvature in the balance.
Well, I was so interested in Alice Chang's talks that I decided to change the trajectory of the series a little bit. And my objective today is to tell you about some results that have an interesting link with the discussion of Poincare-Einstein metrics, although that will only become apparent very late in the lecture. So let me begin by reminding you that on a Riemannian manifold of dimension greater than or equal to 4, the Riemann curvature tensor can be decomposed into a Weil piece, a trace-free Ricci piece, and a scalar curvature piece. And here's literally how you do it. This formula also makes sense in dimension 3, but the difference is that the Weil piece would vanish in dimension 3. It only becomes non-trivial in dimension 4. So there's a piece of the curvature tensor that's represented by that is completely encoded in the Ricci tensor, the trace of the Riemann curvature tensor. Here I use square brackets to denote skew symmetrization, in other words, taking the alternating part. So far this makes sense in any dimension greater than equal to 3. This formula, of course, doesn't make sense in dimension 2, but where in dimension 2 the scalar curvature determines the entire curvature tensor. It's starting in dimension 3 that the trace-free Ricci curvature becomes non-trivial, and then starting in dimension 4 there are all of these pieces. The key point is that the Weil curvature is conformally invariant, namely if you don't raise an index, so you think of it just like the Riemann curvature tensor as being something that is a trilinear map from the tangent space to the tangent space. So you feed it 3 vectors and get a vector back. Then that's literally unchanged if you rescale the metric by multiplying it by a function. So by contrast, the Ricci tensor is very far from conformally invariant. At any given point, you can make a conformal change that completely kills off the Ricci tensor. And the point is that when you do that, the Ricci tensor is the Weil tensor is what's left over. It's the piece of the curvature tensor you cannot get rid of at a point by making a conformal change in a neighborhood. The point is that that when you look at the Hessian of a function that has the same number of components as the components of the Ricci tensor, and then when you actually look at carefully at the rules for conformal transformation. So from what I've said so far, a necessary condition for a metric to be locally conformally flat, in other words, for there to exist isothermal coordinates, in which it looks like the Euclidean metric times a function, a necessary condition is clearly that the Weil tensor must vanish, because you can't get rid of the Weil tensor by making conformal changes. And if it can be conformally rescaled to look like Euclidean space, then the Weil tensor must vanish. But it's a remarkable fact, and much more non-trivial, that the converse is also true starting in dimension 4. If the Weil tensor vanishes, then in fact the metric is locally conformally flat. And that was discovered independently by Hammond Weil and by Élie Carton. They probably could not understand each other's papers and probably did not know that the other person had also proved the result. It took years, in fact, before geometers sort of were able to understand both methods. A little warning, which is not important for this lecture, is that in dimension 3, local conformal flatness is a non-trivial condition. Most 3 manifolds are not locally conformally flat, even though the Weil tensor vanishes in dimension 3. And instead, the Coton tensor is the is the remaining obstruction to local conformal flatness. You can define this Coton tensor in higher dimensions, but it actually is up to a constant, the divergence of the Weil tensor. So the Weil tensor vanishes, the Coton tensor also vanishes. In dimension 3, though, the Coton tensor is an independent object. And the peculiar thing is that it is not determined algebraically by the curvature tensor, but instead is built out of its covariant derivative. So we've just seen that understanding whether a manifold is locally conformally flat is asking whether its Weil tensor vanishes. And so an interesting thing to do is that if you have a fixed manifold without boundary with a fixed smooth structure, you might ask how close to conformally flat can you choose a metric? So there's that's measured by the so-called Weil functional. You can assign to every metric the n/2 norm of the L n/2 norm of the Weil tensor, and this turns out to be conformally invariant. So this is the only power where this functional will actually be conformally invariant. So this is really a function on conformal classes. Then you could think of this as an objective measure of how far a given conformal class is from being conformally flat. And then you could ask the interesting kind of geometrization question: how close to conformally flat can you get on a given manifold? So you could ask, what is the infimum of this Weil curvature? So of course, whenever you have such a variational problem, there are a couple of natural things to ask. This is a non-negative functional, so you could just ask what's its infimum, but you could also ask, are there any critical points? In particular, is there a minimum? Is there a best metric, or is there a metric? It might not be conformally flat, but as conformally flat as possible on your manifold. And of course, then you might be more ambitious after that. Can you classify such critical metrics? Now, for this problem, dimension 4 is exceptional. Of course, it's the first dimension in which this problem even makes sense. In dimension 3, the Weil tensor vanishes. But when you look at this quadratic curvature functional in dimension 4, and look at its Euler-Lagrange equations of the variational problem, then it's actually elliptic with gauge fixing. So if you restrict to metrics with for example, a fixed volume form, and then mod out by diffeomorphisms, this becomes an elliptic problem. So the equation that arises this way is the vanishing of the Bach tensor that Alice told us about. And solutions of the equation, so critical points of the functional are the metrics where the Bach tensor vanishes, and therefore they're called Bach flat metrics, perhaps in appreciation of Bach's mass in B flat minor. But anyway, the Bianchi identities, for example, tell you that any Einstein metric is Bach flat. But of course, being conformally Einstein is also good enough, because this is a conformally invariant functional. You remember in the first lecture, we saw that Einstein metrics in dimension 4 are critical points of any quadratic curvature functional. In particular, this Weil functional is such an animal. By contrast, if you're in dimension 5 or higher, and if you were to look at this variational problem, well, you might be particularly unhappy in dimension 5 because there's that fractional exponent. But anyway, the Euler-Lagrange equations are degenerate. They're quite bad, near places where the Weil tensor vanishes. So this will not really be an elliptic problem in higher dimensions. And even worse, Einstein metrics are typically not critical points of the Weil functional in higher dimensions. If you don't believe me, consider the following example. Take a fixed Calabi-Yau K3 and then multiply it by a torus of the appropriate dimension. All right, so you fix the Calabi-Yau metric. There are Ricci flat Kähler metrics on K3 as I mentioned in the first lecture. Now change the size of the torus. And the most naive thing is just take a fixed flat torus and multiply the metric on that factor by a constant, or if you like, you can vary the lattice. As you do that, these metrics are Ricci flat, right? Ricci flat times Ricci flat is Ricci flat. So this is a family of Ricci flat metrics. They're certainly Einstein. On the other hand, the integrand for the functional doesn't depend on this torus parameter. It actually only comes from K3. And so as you vary the volume of the torus, the integral must change. Right? You're not changing the integrand, but you're changing the volume just by changing the size of the flat factor. And so therefore, that gives you an example of a family of Ricci flat metrics where the Weil functional is not constant. So in general, Einstein metrics are not critical points in higher dimensions. So I'm therefore going to restrict to dimension 4, which was my agenda anyway. One could ask, well, suppose you have a Bach flat metric on a closed manifold, is it necessarily conformal to Einstein? And the answer is certainly not. For example, there is a very large class of critical points given by the anti-self-dual metrics. So a metric is said to be anti-self-dual if W plus, the self-dual Weil curvature, vanishes. In other words, that says that the Weil curvature is the same as its own anti-self-dual part. And if you like, this is saying that so a different way of thinking about the self-dual Weil tensor is you take the Weil tensor, think of that as a two-form with bundle values, and then you take its self-dual part, and similarly the anti-self-dual part would be the anti-self-dual piece of the Weil tensor thought of as a bundle valued two-form. All right, so we saw the signature formula in the last lecture, and the signature formula says that the signature, which is the topological invariant, is up to a universal constant, the integral of W plus squared minus W minus squared. And so that ends up saying that you can re-express this Weil functional in terms of the integral of W plus squared and the signature. And so if you have a metric where W plus is identically 0, that is actually necessarily an absolute minimizer of the Weil functional among all Riemannian metrics, or all Riemannian conformal classes. So anti-self-dual metrics are also Bach flat, and one can also just see that directly, because it turns out the Bach tensor, I wrote it before in terms of a double divergence of the full Weil tensor. It turns out that the double divergence of W plus and the double divergence of W minus plus that Ricci term, those agree. So in fact, W plus alone determines the Bach tensor. Just there's a formula for the Bach tensor just in terms of W plus. So certainly, if W plus vanishes, the metric is Bach flat. Here's a more variational argument. So in fact, up to a factor of 2, you have exactly the same formula for the Bach tensor written in terms of W plus instead of in terms of the full Weil curvature. So an interesting special case of, in case you don't know, people like me and other people spent a lot of time in the late 1980s, early 1990s, showing that many four manifolds have anti-self-dual metrics. But my personal favorite class of examples comes from looking at scalar flat Kähler metrics. So Kähler metrics with zero scalar curvature. So it turns out that if your four manifold if your Riemannian four manifold is actually a Kähler manifold of complex dimension 2, and you give it the natural orientation that's associated with the complex structure, then W plus squared is in fact exactly a certain multiple of the scalar curvature squared. And reaction should be, what? I mean, the scalar curvature is not conformally invariant. The Weil tensor is conformally invariant. How could this possibly make sense? Kähler is not conformally invariant either. If you multiply a Kähler metric by a function, it's almost never another Kähler metric. And so that's why this is even a conceivable formula. Why does it happen? Let's remember that on an oriented four manifold, the two forms split up as self-dual and anti-self-dual forms, and that we can think of the Riemann curvature as a linear map, sometimes called the curvature operator, between two forms and two forms. So in terms of the decomposition of two forms into self-dual and anti-self-dual pieces, we've then discussed the block decomposition of the curvature tensor, and the part that maps the self-dual two forms to the self-dual two forms consists of the self-dual Weil curvature and the scalar curvature over 12 times the identity map. But in the Kähler case, because the almost complex structure is parallel, the curvature tensor, the non-trivial part of the curvature tensor is simply the part that maps 1-1 forms to 1-1 forms. In other words, the curvature operator kills 2-0 forms and 0-2 forms. So if that terminology is not familiar to you, a two form is a 1-1 form if and only if it is invariant under the action of J on two forms. So, but on the other hand, in this setting, when you have even an almost complex manifold, you can carry out this kind of discussion. The 1-1 forms are exactly the sum of the. So this is a rank 4 bundle, and here I'm looking at the real 1-1 forms. That looks like the anti-self-dual two forms plus multiples of the Kähler form. So there is a two form that you get by plugging J into the almost complex structure into one slot of the metric, and so in those terms, this rank 4 bundle splits up as a rank 3 bundle, the anti-self-dual two forms plus the Kähler form. Whereas complementary statement is that so the Kähler form is a self-dual two form. The real and imaginary parts of any 2-0 form are self-dual. So in fact, since the curvature tensor of a Kähler manifold maps 1-1 forms to themselves, when you look at this block decomposition, it means that the block that looks like self-dual Weil plus the scalar curvature times the identity, that only has one non-trivial component, namely the one that maps the Kähler form to itself. So there's just one scalar that determines this entire block of the curvature tensor. And because the trace of this block is the scalar curvature over 4, that missing scalar is the scalar curvature over 4. But then the Weil tensor has to be the trace-free part of that. And what you find is therefore that the self-dual Weil tensor has a repeated eigenvalue of minus the scalar curvature over 12, and then the scalar curvature of over 6 is the other eigenvalue. And now when you compute with my conventions, the norm squared of W plus is just, you take you square this matrix and take its trace. So that gives you scalar curvature squared over 24. So we've seen that for Kähler surfaces, the scalar curvature actually determines the self-dual Weil tensor. In particular here, it determines its norm. If you have a Kähler manifold, you ask, when is it anti-self-dual? When does W plus vanish? That happens if and only if its scalar curvature is identically 0. Now, this is This fits into a general problem in Kähler geometry that has been very active in recent years, trying to understand constant scalar curvature Kähler metrics on a given manifold. However, the fact that in the Kähler case, in complex dimension 2, scalar equals 0 is equivalent to saying W plus is equal to 0. There's a different approach which we were able to pursue in the late 80s and early 90s. So here we're asking about a special case of constant scalar curvature Kähler metrics, but since they're anti-self-dual, it turns out that there's a Riemannian version of Penrose's twistor theory that was first laid out carefully in the Riemannian setting by Atiyah, Hitchin, and Singer, where you can understand anti-self-dual metrics or the conformal classes in terms of a certain complex 3 manifold, which arises as a 2-sphere bundle over the 4 manifold. And in the case of a scalar flat Kähler metric, the extra feature is the twistor space has a canonical. It has a pair of divisors in it, which if you think of the fiber here as representing different metric compatible, almost complex structures at a point, when you have on the Kähler manifold, that J determines a particular section of the twistor space, which turns out to be a complex submanifold. And it also has, there's another, minus J is another section, which sits as another complex submanifold. All right, so in fact, we were able to prove results about scalar flat Kähler metrics. Some of them I just wrote down explicitly, but also there were deformation theory that allowed one to push explicit examples into things that were more complicated. So we actually were able to prove a lot of theorems about constant scalar curvature of scalar flat Kähler metrics that prefigured what eventually turned out to be true more generally of constant scalar curvature Kähler metrics. So if it turns out that if you have a compact scalar flat Kähler manifold, it's either Ricci flat Kähler, so that means it's covered by K3 or a flat torus, or it's rational or ruled with C1 squared negative. So there's a kind of opposite version of the Hitchin-Thorpe inequality, which occurs when you have a scalar flat Kähler metric. In particular, the manifolds that admit these never have Einstein metrics. So if you have an Einstein metric on a 4 manifold, then 2 chi plus 3 tau must be positive, if you like, by inspection of the Gauss-Bonnet formula. But so here are a lot of manifolds that have Bach flat metrics on them that are very far from being Einstein. In fact, there's no Einstein metric on it in these manifolds. It's a topological obstruction. So first in work with Michael Singer, and then with my students Jong-Soo Kim and Massimiliano Pontecorvo, which is misspelled here, unfortunately, I put an extra letter. We proved that if you have any rational or ruled complex surface, then at least if you blow it up at sufficiently many points in well-chosen positions, then you get something which admits scalar flat Kähler metrics. It's not a complete classification, but it's a sort of classification modulo blowing up. All right, so there's another class of anti-self-dual of Bach flat 4 manifolds, the anti-self-dual ones. Now, here's another kind of possibility that could arise. I'll call them double Poincare-Einstein manifolds. So a double Poincare-Einstein manifold is one where you have a metric which can be rescaled by multiplying by a function f to the minus 2, where on the set where f is not 0, this is an Einstein metric, but necessarily with a negative Einstein constant, and where we impose the condition that that this function from m to the real numbers has non-zero derivative along the place where f equals 0. So that means that f vanishes. F is a defining function for a smooth hypersurface, and on the complement of that hypersurface, f gives a rescaling of the metric so that it becomes Einstein. So the way that the way that for this scaling multiplying by f to the -2, the way that the Ricci tensor rescales is that the trace-free Ricci tensor rescales by, well, one thing you do is just a naive rescaling of it, but the other thing is you have to add on twice the trace-free Hessian of the function. So you would be so you could write this equation as saying you have a compact Riemannian manifold, a function f which is which has non-zero derivative along its zero locus, and you impose this condition, which is the condition for saying that when you rescale the metric, you will get an Einstein metric. So here's a simple prototype of this. Just take the force sphere and take there's a defining function then for the equatorial 3 sphere, such that what's left over gets rescaled to 2 copies of the Poincare model of hyperbolic space. So if you take the Poincare model is the standard unit ball in Euclidean space, but of course that's conformally the same as the upper hemisphere of the force sphere times an appropriate function. And what you now can do is glue 2 of those together, and in fact what you get that way is an example of a double Poincare Einstein metric in this sense. Now, this prototype is rather degenerate because, in fact, for example, the force sphere has a different rescaling, which is Einstein, standard round metric, but it's also it's actually conformally flat, so it's also anti-self-dual. So when you're trying to say, well, there are these different kinds, this is not really an example yet. However, we'll see that there are genuine examples that are not degenerate in this sense, that they're not conformal to Einstein, they're not anti-self-dual. All right, so I'm now always working on a compact-oriented four manifold of real dimension 4, and an open problem would be the following. I think the answer to this is probably no. Is every Bach-flat four manifold of one of the 3 types I've just discussed? You can certainly write down examples of things that are Einstein or conformally Einstein. You can write down examples that are anti-self-dual or reversing the orientation self-dual. There are examples that one gets which are double Poincare Einstein. Are there any others? Now, if if you just ask the same question locally, the answer is this is wildly not true, right? You can definitely just, it's almost counting equations. You find that most local Bach-flat metrics on a four manifold, of a small ball in R4, are not cannot be generated by one of these 3 procedures. But so far there is no counterexample on a compact four manifold which would show that the answer is also no in the compact case. So this is an excellent problem where no one has really made any progress on it, and I would love to inspire somebody to go out and solve this problem. Settle it one way or the other. I'm not prejudiced. Whichever way, find the answer, I'll be happy, whether it's yes or no. But today, I'm going to look at the special case. I want to discuss Bach-flat Kähler manifolds. So if you start off with a compact four manifold with a compact Kähler metric, so that's, if you like, a Kähler metric on a complex surface or something of complex dimension 2, and impose these Bach equations, It turns out that any solution is of one of the three types I've just described, either anti-self-dual or conformally Einstein or conformally or conformal to double Poincare Einstein. So the person who pioneered some of these ideas about conformally Kähler Einstein metrics was Andrei Dzerzhinsky, working in the early 1980s. And in the story, the scalar curvature has to play a starring role. After all, I've already told you the scalar curvature of a Kähler surface determines its self-dual Weil curvature. And so you can write the Bach equations just in terms of the scalar curvature. So, in particular, one of the beautiful things that implicitly was discovered by Dzerzhinsky, although he didn't understand it, in fact, the idea had not even emerged yet. Calabi's work was around the same time on when he actually finally wrote his paper on extremal Kähler metrics. Any Bach flat Kähler manifold is, the metric is an extremal Kähler metric. So Calabi wrote a paper in the early 1980s where he finally explained, Yao got him to write it up. He had these ideas that went back to the 1950s, but which he had never clearly explained. And what always happens is somebody says, well, why don't you write up all of those ideas? And you find you prove new theorems in the process. So this is a wonderful paper, very influential paper called Extremal Kähler Metrics by Eugenio Calabi. In Calabi's definition, an extremal Kähler metric on a compact manifold, and you would do this in any dimension. You can look at this functional, the integral of the scalar curvature squared, and think of that as a functional not on all metrics, but on the set of Kähler metrics in a fixed Kähler class. All right, so you have a fixed cohomology class in H2, and it's actually an H11 for the fixed complex structure. Then there's a dictionary where every positive 1-1 form in that cohomology class corresponds to a certain Kähler metric. And Calabi studied the variational problem for the integral of the scalar curvature squared. Now, the Euler-Lagrange equations of this are fourth order, but on a compact manifold, they are always equivalent to a critical point turns out to be equivalent to satisfy the property that the 1-0 part of the gradient of the scalar curvature is a holomorphic vector field. So if you forget, I mean, if you just identify the 1-0 tangent bundle of a complex manifold with the ordinary real tangent bundle, it's saying that the gradient of the scalar curvature is a holomorphic vector field. It has a couple of other geometric meanings. A different way of saying this is that the Hessian of, in other words, the second derivative of the scalar curvature with respect to the Riemannian connection, the Levi-Civita connection, is J invariant. Okay, so if it's J invariant, that means that this would correspond to a 1-1 form, and in particular, the piece that would correspond to d bar of the gradient of S vanishes. And from the Riemannian point of view, there's another equivalent condition. It's saying that when you take the gradient of S in the ordinary real sense, apply J to it, that's actually a killing field. So in this situation, you could say, well, you're thinking of the Kähler manifold as a symplectic manifold. Think of the scalar curvature as a Hamiltonian that also gives a certain vector field, which geometrically is the same as take the Riemannian gradient and apply J to it. Well, you could do that for any function on a symplectic manifold. The magic here is that that's not just, doesn't preserve just the symplectic structure, but it preserves the metric, preserves J and the symplectic form, and therefore preserves the metric. Shushang Chen proved a wonderful result that actually, so Calabi described these as extremal Kähler metrics, but actually, I mean, that's critical points of this functional. And you might hope that they're minimizers. That was eventually proved by Shushang Chen. Extremal Kähler metrics are always minimizers of the Calabi functional in the Kähler class. And Donaldson and various other people then proved a uniqueness result. I mean, I should mention there were other people involved in the final theorems. Mabuchi played a role, so did Shushang Chen, so did Gang Tian. But really the breakthrough was Donaldson's. So extremal Kähler metrics turn out to always to be unique modulo biholomorphisms in any Kähler class on any complex manifold. All right, so the punchline was that, you know, the variational problem we've been looking at is critical points of the integral of W plus squared on the space of all metrics. If you have such a critical point, I mean, in particular, if you now restrict to those metrics that are Kähler metrics in a fixed Kähler class, it has to be a critical point of that restricted functional. But on the Kähler class, on the Kähler metrics in the fixed Kähler class, the functional you're looking at is essentially Calabi's functional. Now, in addition to being able to vary a Kähler metric in its Kähler class, you can also vary the Kähler class in H11, which is the subspace of the second cohomology, which is annihilated by the holomorphic 2 forms. This turns out to be on a Kähler manifold. This is exactly the same as those those cohomology classes which are represented by 1-1 forms. So you can think that, well, there's a positive cone. There's a cone in H11 called the Kähler cone that consists of those cohomology classes which arise from the various Kähler metrics. That's an open cone, open convex cone in H11. And there's a certain function on it that one can define, which I call the virtual action. This is all now in complex dimension 2. The virtual action is built out of 2 pieces. One involves something you could just write down kind of almost topologically. You take a Kähler class, you take its intersection pairing with the first Chern class, you square that and divide by the Kähler class squared. And so that roughly, this actually in the Kähler case corresponds to that thing I was calling C1 plus in the last lecture. But then there's an extra term built out of the so-called Futaki invariant. I'm not going to go into the details of what the Futaki invariant really is and what is this norm, but the point is that there's something that's naturally defined in terms of the complex structure. Without knowing the metric, you can, in fact, there is something you can assign to a Kähler class where you can actually write down explicit formulas in concrete cases where the meaning of this expression actually is, if I had an extremal Kähler metric in that Kähler class, what would its Calabi action be? What would be the integral of the scalar curvature squared? So for an extremal Kähler metric, up to a factor of 32 pi squared, the integral of s squared is, for an extremal Kähler metric, just this expression. It just depends on the Kähler class. All right, so the basic proposition then is that if you have a Kähler metric on a compact complex surface with Kähler class omega, then that metric is Bach flat if and only if, first of all, it's an extremal Kähler metric and it's a critical point of this virtual action. So the extremal condition is saying that in its own Kähler class, it's minimizing the integral of scalar curvature squared. And then there is this openness property about extremal Kähler metrics. If you have an extremal Kähler metric, then nearby, you in the adjacent Kähler classes, you also have extremal Kähler metrics, and they actually form a nice family. So in fact, this virtual action then literally becomes the integral of the scalar curvature squared for those up to times a constant for these metrics. And so you have to both be a critical point in your Kähler class and then all among nearby classes. Okay, so if you can, the nice thing is that there's sort of, this breaks the problem into two different pieces. Which Kähler classes are represented by extremal Kähler metrics and which classes are critical points of the virtual action. And you can, in principle, treat those two questions separately. So the objective today is to show you that if you have a Bach flat Kähler surface, then it's one of the three types I described. And here's the main theorem. If you have a compact connected Bach flat Kähler surface, then exactly one of the following three conditions holds. The first possibility is that when you look, it's an extremal Kähler metric, and it's scalar curvature, some function on the manifold. The key thing to ask is what's the sign of the minimum of the scalar curvature? If the minimum is positive, then either you're looking at a lambda positive Kähler-Einstein metric, or if you multiply your Kähler metric by the scalar curvature to the -2, then that conformally related metric, it's not Kähler anymore, it's only conformally Kähler. That new metric is an Einstein metric with positive lambda, but it's very far from its holonomy is actually SO4. It's the full rotation group. If the second possibility is that the scalar curvature could be identically zero. All right, so in particular, this is the case where the minimum value of the scalar curvature is zero. But in that case, it turns out the scalar curvature has to be identically zero. So in this case, either you're looking at a Ricci flat Kähler metric, so you're on K3 or the 4 torus or something that's finitely covered by one of those. But the other possibility is that you have something which is a scalar flat Kähler metric, which is not Ricci flat. And in this case, the metric is still anti-self-dual, but it's not Einstein. The third possibility is the minimum value of the scalar curvature is negative. So in this case, again, there are two different possibilities. You could be looking at a Kähler-Einstein metric. And in this case, the Kähler-Einstein metric would have negative lambda. So in particular, in that case, the scalar curvature is always negative. It's actually constant. But then there's the other possibility that when you multiply, it turns out that the other possibility is that the minimum of the scalar curvature is negative, but the maximum of the scalar curvature is positive. And now when you multiply the metric by the scalar curvature to the -2, you get a double Poincare-Einstein metric. So in this case, one can show that the locus where the scalar curvature vanishes is a smooth, connected 3-manifold, and the two pieces it cuts the 4-manifold into are both connected. All right, so this is a good place for our intermission, and I'll start again in about 5 minutes.
Thank you very much. If there are questions.
Yeah.
So
in fact, it's also the next page. So I was going to start with a repetition of the last page. So it's easy to go forward.
So I have a question. So are there any known obstruction with a manifold is compact or non-compact to the just existence of a back flat metric?
No. So this is an interesting, good question, because just so far in terms of for example, one obstruction to the existence of an Einstein metric is the Hitchin-Thorpe inequality. And as I just pointed out, actually for these scalar flat Kähler metrics, you get another a similar inequality, but with the other sign. So it starts sounding like, well, maybe, sort of that kind of obstruction is not possible. There's not a generalization of Hitchin-Thorpe. We really don't know. And so I think that this is a very, very rich open area of differential geometry or in geometric analysis. I think the most promising thing to try to do is just find some ways of producing new Bach-flat metrics that don't come from any of these kinds of constructions I've been talking about. So, of course, it turns out that huge, I mean, in a certain sense, most manifolds have anti-self-dual metrics. That's modulo blowing up a lot. But for a specific manifold, I mean, there are definitely obstructions to having anti-self-dual metrics. For example, if there's an anti-self-dual metric, the signature has to be negative. So, and as I'll explain in the next lecture, one expects that there are other obstructions too. But it could be that the obstructions to finding even these flavor of Bach-flat metrics, even if you only look at these three classes, it might. There's no theorem I know of that would say that there are manifolds that don't admit any of them. Yeah, so that's a great question. And I hope someone in this room will find the answer.
Other questions?
On a complex surface, you could expect there might be uniqueness of the Bach-flat, of a Bach-flat Kähler metric.
Well, not in general. So the classes that I've talked about. So, for example, if you look at Kähler-Einstein metrics, I guess, are you saying you fix the complex structure?
Yeah, I think the complex.
Yeah. So in fact, that's not true in the anti-self-dual case. So what happens when you look at the case if you just have scalar flat Kähler metrics, then the integral of the scalar curvature is a function on the Kähler cone, and so you get a hypersurface in the Kähler cone that is where the integral of the scalar curvature is equal to 0. It turns out with a couple of, if you assume there are no holomorphic vector fields, for example, then if you take a given scalar flat Kähler metric, you can find nearby ones by moving the Kähler class in that hypersurface. So if beyond just fixing the complex structure, you also fix the Kähler class, then you're in territory where it becomes more plausible. But it's the main problem is that we have a class of Bach-flat Kähler metrics where we know less, and so there's still a problem there. Also, in the case of, for example, Kähler-Einstein metrics with lambda positive, and also these conformally Einstein metrics with lambda positive, there are cases where the space of holomorphic vector fields is non-trivial, and then you can move. It turns out not every holomorphic vector field generates isometries, so you can have complex automorphisms that don't preserve the fixed metric. So, but that would just, you'd say, well, they're morally the same metric. You've just moved it by holomorphic vector field or by a complex automorphism. So yeah, your question is a very reasonable one. We don't have an answer, but it's a good thing to think about. All right, so at this point, I've described the statement of the main theorem, that if you have a Bach-flat Kähler metric on a compact complex surface, then there are three different basic types, but actually within each of those three basic types, you have to distinguish between the Kähler-Einstein metrics, which are obviously examples, and other things. So let me then point out, it was implicitly said before, that the trichotomy here has to do with the minimum value of the scalar curvature. So if you if the minimum of the scalar curvature is positive, then in fact you can rescale to get a conformally Kähler-Einstein metric on the manifold. If the scalar curvature is if the minimum of the scalar curvature is 0, then in fact it's identically 0. And in that case, the metric is actually anti-self-dual. And then finally, if the minimum of the scalar curvature is negative, then there are two cases. Either it's constant and negative, in which case the metric is Kähler-Einstein, or it changes sign and then it gives rise to a double Poincare-Einstein metric. So, so either the scalar curvature is positive everywhere, or it's identically 0, or it's negative somewhere. Now, if we rule out the Kähler-Einstein case, if we just arbitrarily throw it out, then the way the trichotomy works is that either you have by multiplying the metric by the inverse of the scalar curvature, if it's positive, you get a compact Einstein manifold, which is not Kähler. Or F is identically 0, and in that case, the manifold would be a scalar flat Kähler, but not Ricci flat. And then the last possibility is that the scalar curvature actually changes sign. Its minimum is negative, its maximum is positive. So let me now tell you what we know about these various cases. Let's first look at the case when the scalar curvature is positive. This happens if and only if, well, in the standard shorthand, C1 is positive. Now, the first Chern class is not a number. When you say it's positive, you're saying that it's actually a Kähler class. This inequality sign is actually a partial ordering where something becomes larger if you add on a Kähler class. So C1 positive is exactly saying that C1 is a Kähler class. The manifolds of complex dimension 2 with this property, in general, in higher dimensions, one would call them Fano manifolds, but it turns out that Fano also did something on complex surfaces, and it's a bad idea to call them Fano surfaces, because Fano surfaces can mean something else. Instead, the name we attach to it is that of Del Pezzo. Del Pezzo surfaces are those compact complex surfaces for which the first Chern class is a Kähler class. So these can be classified just by some now rather classical but very beautiful algebraic geometry. The possibilities are that either you have CP2 blown up at K points in general position, where K can be from 0 up to 8, or CP1 times CP1. So for example, if you blow up CP2 at 3 points, which are not collinear, there that would already be in so-called general position. That would be an example of a Del Pezzo surface. So blowing up, let me remind you, is this process where you take a compact complex surface, you replace a point with CP1, and then in terms of the change of the diffeotype, you've taken a connected sum with a reverse-oriented CP2. And the model for the blow up is that the local model is you're thinking of the blow up of C2 as the O-1 line bundle over CP1. All right, so to make this a self-contained definition or result, we have the blow up of CP2 at K points in general position, and technically what general position means is that no 3 of them are on a line, no 6 of them are on a conic, and no 8 of them are on a nodal cubic with one of the points at the node. So these conditions are imposed so that, for example, if you blow up at 3 points on a line, there will be, when you take the proper transform of the line, it will have self-intersection -2. And that then by the adjunction formula means that C1 isn't positive anymore. So these conditions are, it's more obvious that these conditions are necessary, but then there's converse constructions you can prove that they're also sufficient. All right, so by the way, the way that the algebraic geometers would prefer to phrase this statement, it's the same as saying that the anti-canonical line bundle is ample. All right, so the basic existence theorem here is that every del Pezzo surface, so here I'm thinking about not just the topological type, but also the fixed complex structure. So for each del Pezzo surface, there is a J-compatible, conformally Kähler Einstein metric on it. And this metric is unique up to complex automorphisms and constant rescalings. So in other words, every del Pezzo surface has a geometrically uniquely defined Einstein metric on it, where you think of two Einstein metrics as the same if you've multiplied it, just taken them, normalize the volume to be your favorite positive number to get rid of rescalings. And then complex automorphisms are in particular diffeomorphisms. So the other thing you can do is pull back via complex automorphism. So the history of this theorem is a rather long one. The first example of such, I mean, there are a couple of obvious things. CP2 with its Fubini-Studi metric, that's an Kähler-Einstein del Pezzo surface. S2 times S2, or CP1 times CP1, with its product metric, you take two unit two spheres with standard round metrics, multiply them together, that's a Kähler-Einstein metric on a del Pezzo surface. But the first really non-trivial example was actually found by a student of Hawking named Don Page. Had no idea that it had anything to do with Kähler geometry. It was Dzerzhinsky that noticed that Page's metric was actually conformally Kähler. In fact, it's conformal to one of the metrics that Calabi constructed. Calabi found on the blowup of CP2 at one point, he constructed a one-parameter family of extremal Kähler metrics. And that's in this landmark paper I mentioned. And actually one of those turns out to be conformal to Page's metric. So the mathematical community, the sort of hardline Kähler geometers were completely ignorant actually of this Page and Dzerzhinsky work. When I first mentioned this to Yao, he thought that was a very strange thing. Oh, it can't be interesting. It can't go anywhere. There's just isolated weird case. Then Hsu showed that, for example, CP2 blown up at 3 points in general position admits a Kähler-Einstein metric, and he also showed that if you look at the Fermat cubic, it has a Kähler-Einstein metric. Then Tian and Yao constructed for each of the topological types, showed that the sum of the del Pezzo surfaces of each topological type admit Kähler-Einstein metrics. Tian then announced and published a proof in Invenciones, a very difficult paper to read, claiming that each of the del Pezzo surfaces carries a Kähler-Einstein metric. And it only became clear many years later that this was an example of proof by intimidation. The reason that it was so hard to read is actually part of it's wrong. So this result is always ascribed to Tian, but in fact his paper has significant mistakes in it. The basic strategy is fine, but the first paper where the strategy is correctly carried out is a paper of Odaka, Spotty, and Son. They're very polite. They don't mention that they're correcting Tian's mistakes, but they have other results too. In the meantime, there had been other proofs of this theorem in the Kähler-Einstein case. So most of these cases, notice this first example, which was thought of as an isolated curiosity, is not a Kähler-Einstein metric. But it turns out to be conformally Kähler. And then in 2008 with Shusheng Chen and Brian Weber, we proved the existence of such a metric on the remaining case, which was CP2 blown up at 2 points. So here again, the metric is conformally Kähler, but not Kähler. In terms of the uniqueness, there's a beautiful general result of Bondo and Mabuchi proved in the late 1980s about uniqueness of Kähler-Einstein metrics on Fano manifolds, and in particular, this would, for example, tell you on CP2 blown up at 3 points in general position. There is a family of Kähler-Einstein metrics, but they're actually all the same up to automorphism. And then, well, first of all, as soon as you allow things that are not Kähler-Einstein, it broadens the question. For example, it was conceivable that on CP2 blown up at 3 points, maybe there's another Einstein metric which is conformally Kähler, but not Kähler-Einstein. It turns out that doesn't happen. So in a paper in JDG in 2012, I proved that each of these metrics is actually unique up to rescaling and automorphism for fixed complex structure. All right, so one reason that I really found that result very satisfying is that in my paper with Chen and Weber, we also gave the following theorem. Suppose you have a smooth, compact, oriented form manifold which carries a symplectic form. It's a symplectic form manifold. And suppose now forget about, for a moment, just forget about the symplectic form and say, well, it's a smooth manifold. Does that smooth manifold admit an Einstein metric with lambda positive? So here you have a symplectic structure, you have a metric, an Einstein metric. They live in the same building. Maybe they've never met. Maybe they once were in the elevator together and just didn't like each other very much. But anyway, so here there's no assumption that the symplectic structure and the metric have anything to do with each other. But if you just assume those two things, the manifold admits a symplectic structure, admits an Einstein metric with lambda positive, then you can prove that up to diffeomorphism, it is a Del Pezzo surface. It's either CP2 connected some K CP2 bars where K is 0 to 8, or it's S2 times S2. So this theorem involves two completely different pieces. So as I mentioned, we had proved finally the missing piece that there were no obstructions to finding positive lambda Einstein metrics on these manifolds. These also arise as Kähler manifolds. They all have symplectic structures. But also you can conversely show, if you have a simply connected form manifold which has a symplectic structure and a metric of positive scalar curvature, it turns out these are the and it satisfies the Hitchin-Thorpe inequality, then it's one of these. What I mean is that the Einstein metric is allowed to have something to do with the symplectic form if it wants to, but a priori, it could be just something completely unrelated. So in fact, in the construction, since we construct the Einstein metric, the Einstein metrics that actually I've described on these manifolds previously were all conformally Kähler, and a Kähler metric has a preferred symplectic form. It's the Kähler form. So you have those two things, and it would be a much easier theorem it would involve different ideas just to say, well, if it's conformally if it's conformally Kähler and it's Einstein, then it's one of these. But in fact, what I'm trying to say is that you get a strict list without assuming any relationship at all between the metric and the symplectic form, merely the existence of an Einstein metric with lambda positive and a symplectic form. Okay, so for the examples of Einstein metrics with lambda positive that we know on these manifolds, then in fact you could take the symplectic form to be the Kähler form, but that's not assumed in the result. All right, so the case for Bach flat form manifolds where the minimum of the scalar curvature is positive are exactly the Del Pezzo surfaces. Every Del Pezzo surface admits such a an Einstein metric, but still there is a there's a dichotomy here that's still left, or two subcases. One is the Kähler-Einstein case. Kähler-Einstein, most of these turn out to be Kähler-Einstein, but there are two exceptional cases. So that happens if the automorphism group of the manifold is trivial, or more generally, if it is reductive, which is a fancy word for saying that the automorphism group is the complexification of a compact Lie group, which is eventually the isometry group of the metric. Isometry groups of Riemannian manifolds are always compact. In the case when the automorphism group of the manifold is reductive, then in fact the metric turns out to have to be Kähler-Einstein. In the case when it's non-reductive, one gets these conformally Kähler-Einstein metrics on the two exceptional cases of CP2 blown up at 1 point or 2 points. All right, so that was the case when the minimum of the scalar curvature for your Bach flat Kähler metric is positive. In that case, s to the -2 is a perfectly good conformal factor, and that turns out to be the magic conformal factor that maps you to an Einstein metric. So the next possibility is the scalar curvature could be identically 0, and then these are so-called scalar flat Kähler metrics. And again, there are two cases. It could be a Ricci flat Kähler metric, or it could be a non-Ricci flat scalar flat Kähler metric. So I previously discussed this. It's the case when W plus is identically 0. So the main point of this theorem is that if the minimum, this part of the theorem, which is one of the nicest, in my own opinion, is one of the nicest arguments in the article, is that if the minimum of the scalar curvature is 0, then the scalar curvature is identically 0. So in the first case, the Kadeira dimension would be 0 for a K3 surface. Or for a torus, the Kadeira dimension is 0, whereas it's -infinity in the second case. Kadeira dimension is -infinity in case Roman numeral 1. So in the Kadeira classification of compact complex surfaces, Kadeira extended ideas of Enriquez from the early 20th century to give a rough classification of complex surfaces, sort of sorting them into basic baskets. And so the key invariant that one wants to understand is the so-called Kadeira dimension. The Kadeira dimension of a compact complex surface is you take the lim sup as L goes to infinity of the log of the dimension of the space of holomorphic sections of the Elf power of the canonical line bundle. So this is asking, the canonical line bundle has sections, the two forms, and this is looking at generalizations of things that locally look like holomorphic products of holomorphic two forms, tensor products of them. And then you divide by log L. So that looks impenetrable, but what you're actually asking, it turns out that this number grows in a polynomial way, and you're asking what's the degree of that polynomial. So you can define this Kadeira dimension actually in higher dimensions too. What you do is there's a so-called canonical line bundle, which is the bundle of M0 forms. So if you had a holomorphic M form on a complex M manifold, that would be a section of the canonical line bundle. You look at tensor products of the canonical line bundle, ask how many sections they have. But the surprising thing is that this Kadeira dimension is always either -infinity, as you know, the lim sup would be -infinity if these dimensions were all 0. But the other possibilities are that it is an integer between 0 and the complex dimension. So the geometric explanation of, I mean, this looks like just gibberish, right? But what it's actually asking is that among all of these so-called pluricanonical line bundles, you take a power of the canonical line bundle, you look at its space of all holomorphic sections, and that is trying to define a map to a projective space by looking at ratios of sections of these line bundles. So then what you can do is say for among all of those maps, which has for which value is the dimension of the image the largest? That's some integer no bigger than the complex dimension, and that integer is the Kadair dimension. Okay, here there's a peculiar convention that to make this a true statement, one defines the dimension of the empty set to be minus infinity. What's the dimension of the empty set? What's the dimension of the empty set? I mean, it doesn't really, any statement you could make about the empty set is true. So here's a true statement: the dimension of the empty set for these purposes is minus infinity. And so that corresponds to the case when there are no holomorphic sections and the map is kind of the empty map. So in general, these maps are only defined on a certain subset, namely outside the points where all sections of the given line bundle vanish. All right, so in terms of the sort of getting a sense that these have to do with very different worlds in terms of complex geometry. In case one, everything has Kadair dimension minus infinity. In case two, things in the second basket have Kadair dimension minus infinity, but things in this case, in the Ricci flat Kähler case, that's where the canonical line bundle is trivial and the Kadair dimension is 0. Then in the case when the minimum of the scalar curvature is negative, then again we have the case where we either get a Kähler-Einstein metric, or it turns out that the zero set of the scalar curvature is a smooth hypersurface, and by multiplying the metric by the scalar curvature to the -2, we get a double Poincare-Einstein metric. So here the key point is that if the minimum of the scalar curvature is negative, then either the scalar curvature is constant or it changes sign, and that's the distinction between these two subcases. And so the first subcase, the Kadair dimension would be 2. In the second subcase, is again minus infinity. Kähler surfaces with Kadair dimension minus infinity are rational or ruled. They're either CP2 or a CP1 bundle over a complex curve, or blowups of those. So Kadair dimension minus infinity is a very, very powerful piece of information about a complex surface. You kind of already know roughly what it must look like. In terms of specific, there are specific examples that show that this case 3B really does occur. Wang and Simonka, actually had found examples. They sort of formulate the problem in a very strange way. You wouldn't realize it's a discussion of Bach flat Kähler metrics, but they actually did write down some examples. And then my student Christina Tennyson-Friedman wrote down a huge number of other examples. In both cases, they applied a certain variation, kind of a direct variational approach to find these things, but it'll turn out, as I'll explain later, that actually you could have just written down these examples without doing any work, and I'll explain them later. So a few words about how do you prove this theorem. For Kähler metrics, the Bach tensor turns out to be expressible in terms of, for any Kähler metric, then you could write, remember W plus is determined by the scalar curvature. And if you look at the formula for the Bach tensor in terms of W plus and the trace-free Ricci curvature, it turns out that the Bach tensor is up to a factor. You take the scalar curvature times the trace-free Ricci curvature, and then you add on the trace-free Hessian of the scalar curvature, and then you have to move that by J and multiply it by a certain factor. That's for a general Kähler metric. But then in the case when it's extremal, the trace-free Hessian is actually J invariant, so this simplifies. So you see here from this that Bach flat does imply that it's extremal, but because that would end up saying that this trace-free Hessian has to be J invariant. So if you have a Bach flat Kähler, a key lemma for the whole thing is that if you have a Bach flat Kähler metric where the scalar curvature is not constant, then actually the scalar curvature is a so-called Morse-Bott function on the manifold. It's not so, an ordinary Morse function is one with only isolated critical points where the Hessian is non-degenerate. Morse-Bott allows the possibility that the critical point could actually be a submanifold, and then the Hessian is merely non-degenerate in the transverse direction. Okay, so the reason that this holds is that we're actually, when you take for an extremal Kähler metric, when you take J times the gradient of the scalar curvature, that's a killing field. And this is really a statement about, well, killing fields only vanish on totally geodesic submanifolds. But you have more information here, actually. It turns out that the zero sets are either complex curves or isolated points. So in particular, one thing that follows from this is that if you have a critical point, then the Hessian of the scalar curvature is never zero, okay, at a critical point. So in particular, that tells you that at a minimum of the scalar curvature, or at a maximum of the scalar curvature, the Laplacian of the scalar curvature is actually necessarily non-zero, because at the minimum or the maximum, the Hessian has a sign, and it's not identically zero, and therefore you find that at a minimum or maximum, the Laplacian of the scalar curvature is not zero. All right, so so in fact, in the extremal case, the Bach-flat form, the formula for a Kähler metric to be Bach-flat is just that 0 is equal to the scalar curvature times the trace-free Ricci curvature plus twice the Hessian of the trace-free Hessian of the scalar curvature. But that's actually just this is really an observation of Dzerzhinsky's. This comes down to saying that at the set where the scalar curvature is not zero, s to the minus 2g is an Einstein metric. All right, so either the really bad case is when the scalar curvature is identically zero, then you don't get an Einstein metric anywhere. But otherwise, you would get an Einstein metric on the complement of the zero set of the scalar curvature. So now the trick is to look at the function. So remember, my convention about the Laplacian is it's the geometric one, which has positive spectrum, minus the trace of the Hessian. So if you look at this this function, which is minus 6 scalar curvature, Laplacian scalar curvature, minus 12 gradient of scalar curvature squared plus s cube, that's actually that's what the scalar curvature would be for this Einstein metric. But that's certainly a smooth function on your manifold. And so the lemma, a key lemma, is that this function is actually necessarily constant. So obviously, in a region where you've rescaled to get an Einstein metric, it must be locally constant there. But you might worry, well, maybe there could be different domains where the constant takes value. But of course, this is a smooth function. So anyway, this turns out to be a constant on the manifold, and its sign is the same as the minimum value of the scalar curvature. So you just evaluate this so if s is constant, this is obviously you're done. If s is constant, you just look at, oh, that's constant too, isn't it? But if otherwise, at the minimum of the scalar curvature, you find, well, that that the scalar curvature times s squared minus 6 times Laplacian of s is so this thing is necessarily, at a minimum, that would be positive, and so k is a positive number times the scalar curvature. So this kappa and the scalar curvature have the same sign at the minimum of the scalar curvature. And on the other hand, kappa is constant. Okay, and then so this is a constant function, and in fact, it really represents the scalar curvature of the rescaled metric when that makes sense. So I mentioned that if the minimum of the scalar curvature was 0, then in fact the scalar curvature would have to be identically 0. And the reason that that happens, this is the same as saying that when you look at the formula for kappa, this is the same as saying that, remember, if the minimum of the scalar curvature is 0, kappa has the same sign, so kappa would have to be 0. Kappa is really the sign of the Einstein constant for this rescaled metric. So you want to show that this implies that the scalar curvature is constant. So if not, the scalar curvature equals 0 would have to be a finite set, because we have this equation. We know that the Hessian is where S is 0, this would have to be a critical point. The Hessian has a sign, and you then find that the trace-free Hessian has to vanish at this point just by looking at the equation. If scalar curvature is 0 at that point, this means that the trace-free Hessian of the scalar curvature vanishes. But we know the full Hessian is not 0, so that means it's a multiple of the metric. And now, because this is a minimum, you also know that constant is actually positive. So you end up finding that the other alternative would be that there would be a finite number of points where the scalar curvature was 0. And then on the complement of that set, your rescaling would give you an Einstein metric outside a finite number of points. So, but kappa is 0, that means that that's a Ricci flat Kähler metric on the complement of these points. And it's a Ricci flat Kähler metric, which is asymptotically Euclidean. So, there's a notion of an asymptotically Euclidean manifold, which would be that you have a manifold with a finite number of n's, and each of those n's has a diffeomorphism to Euclidean space minus a ball. And then you have some fall off of the metric. Here, these are the minimal condition would be so-called Crucial fall off. So in this case, if the scalar curvature did not vanish identically, but its minimum was 0, then what you would get after throwing out finitely many points, you rescale and you get a complete Ricci flat manifold. But then one has the positive mass theorem, or you could also do this by Bishop-Gromov more directly. So the point is that when the manifold is Ricci flat, it's an observation of Bartnik that forces the mass to vanish. And here you have something which is asymptotically Euclidean. It would have 0 mass. Positive mass theorem says it must be Euclidean space. Now you could also do this. Bishop-Gromov for Ricci flat manifold says the volume growth has to be less than or equal to that of Euclidean space, but in the asymptotic Euclidean place, it has to be equal. So you could also just read off directly from Bishop-Gromov that if you have a Ricci flat manifold, which is asymptotic Euclidean, it's flat space. All right, but on the other hand, for flat space, W plus is identically 0. But the set that we threw out was the set where W plus vanishes. So we have a contradiction, right? That can't happen. So the only possibility is that if the minimum of the scalar curvature is 0, then in fact the scalar curvature is identically 0. All right, so then we had the remaining case is more mysterious. So the other cases, we kind of understand all of the other possibilities very well. But the final case is maybe we're in this case where the scalar curvature changes sign. So here, the claim is that, in fact, if the minimum of the scalar curvature is negative and the metric is not Kähler-Einstein, so the scalar curvature is not constant, then in fact the maximum of the one key point is this maximum of the scalar curvature has to be positive. If it weren't, then when you take this rescaling, if the maximum of the scalar curvature was negative, S the minus 2G would be defining a global Einstein metric on this compact manifold that has a killing field, because you originally had a killing field for the unrescaled metric, but you're rescaling by a function of the scalar curvature, and so this turns out to still be a killing field. And Bachner says you can't have the Bachner argument, the less well-known aspect of his original paper, where he also studied harmonic one forms, but he also studied killing fields and observed that if the Ricci curvature of a compact manifold is negative, there can't be killing fields. So that already tells you the maximum of the scalar curvature is greater than or equal to 0. But on the other hand, when you look at the formula for kappa, it would have the property that, well, if the maximum was 0, then at 0, this you'd be at a critical point. That would vanish. That would vanish. We've got a contradiction with the statement about the at a maximum, this has a sign. So you find that actually that argument, moreover, shows you that along the locus where the scalar curvature vanishes, the gradient of the scalar curvature must be non-zero everywhere. So in other words, S equals 0 is a smooth hypersurface. And so we still have more information, though. We know that the scalar curvature is a Morse Bott function with critical points of only without any critical points of odd index. They all have even index, and that's because the Hessian of the scalar curvature is J invariant, as I mentioned before, for an extremocalar metric. And so it turns out you can read off from that the region with scalar curvature negative and scalar curvature positive, those are both connected. So you could use you can replace S with minus S, and you're really asking, what happens in terms of connectivity of sublevel sets of a Morse function if there aren't any critical points of index 1. You can't change the number of connected components. And similarly, you could ask how are the level sets of this changing as you pass critical points, and it turns out you're doing a knot surgery. It turns out you must have all the level sets are connected. In particular, S equals 0 is connected. All right, so that's some information. But we don't know very much about this last case. It can't be excluded because, in fact, there are examples, as I mentioned, found by Wong Samanka and by Tennyson Friedman, where the last is a single person, not two people. So the funny thing about these examples, they were actually, proved to exist by sort of complicated calculations. But if you stare at them and you know the right things, you realize that actually in this last case, the double Poincare Einstein examples, even though they were discovered in this kind of complicated indirect way, just using the general theory about trying to find extremocalar metrics with certain properties, they're actually doubles of known Einstein manifolds constructed by physicists, the so-called ADS tau bolt metrics. And so what actually is happening in these known examples is that you take two copies of an ADS tau bolt metric. These have well-defined conformal infinities, and you glue them at conformal infinity, and it turns out that it's smooth across. You reverse the orientation of one. So these actually have an orientation reversing self-diffeomorphism that's in fact a conformal isometry. So in particular, these are manifolds with zero signature. They correspond to minimal ruled surfaces. And so the mystery is whether this is the general fact. In particular, if you could just prove the signature is a priori 0 in this last case, I believe one could push through a proof that the known examples are all that occur. But at any case, certainly topologically, they are the typical things. So, so the question is should the signature vanish for some a priori reason? Now, this is actually exactly related to the subject of Alice's talks, because here's a question where you have a particular conformal infinity, and it's bounding two different Poincare Einstein manifolds that even talk to each other nicely across conformal infinity. under these circumstances, you have some extra information. Can you prove that the fill-in is actually the same on both sides? So that may be a very hard problem, but I think it's a good one. And so maybe more progress on this problem should be arrived at by trying to consider this uniqueness problem for Poincare-Einstein fill-ins given a fixed conformal infinity. I'll stop there for today.
So are there any questions?
So what can you, is it on? Okay. Oh, what can you say about the induced metric? So before you multiply by the negative power of the scalar curvature, what can you say about the induced metric on the zero set of the scalar curvature?
So one of the most important things is that you have this killing field, which is you take the gradient of the scalar curvature and then apply J to it, and that's now tangent to the level sets of the scalar curvature. So in particular, this is this manifold a priori has a killing field. So of course you could you know for general reasons that the entire Weyl curvature vanishes, the four manifold vanishes along this hypersurface, but that's not much help in understanding the intrinsic geometry.
Yeah.
If you normalize that killing field is everywhere non-zero, and if you rescale the metric so it has constant length, then you can relate the sign of the Ricci curvature in that direction to whether as a CR manifold, whether it's pseudoconvex or not. So there are various intriguing facts one knows, but really a lot's up in the air. So the main thing I would point out is that it has a killing field, and also, after all, it's a hypersurface not just in a manifold with a Riemannian metric, but also in a complex manifold. So it has an induced CR structure. That CR structure is invariant under this killing field also. There are some intriguing things to say about it, but I'm not sure what should be emphasized, what might give you some hope of finding out more information. In terms of the known examples, there are certain cases where that hypersurface is either a three-sphere or a lens space. And so that would be something with a positive sigma constant, positive Yamabe invariant.
Mm-hmm.
But then there are other cases where it's a circle bundle over a surface, and then for those the Yamabe invariant of the three manifold is actually going to be zero.
Okay.
It won't be positive in that case. So it might be a little bit, if you were to assume that the manifold, if you assume your four manifold is simply connected, then I believe you can show that this three manifold would have to be a lens space. But even that, I mean, I think there's some details to fill in.
Any other comments or questions?
So, suppose you have an example of a Bach flat metric, which is not the type you describe, which is not Weyl Schaff dual, anti-Schaff dual. What does that say about your double Poincare-Einstein?
Well, so the fact that for a double Poincare-Einstein metric that it's Bach flat is really because on a dense set this is conformally Einstein. You know that Einstein metrics have vanishing Bach tensor, so by continuity, the Bach tensor identically vanishes for a double Poincare-Einstein manifold.
So that
those,
metric also introduced in this doubly Poincare-Einstein metric.
yeah, so those are all Bach flat too. And so, I mean, in a certain sense, you might say, well, those are morally just like conformally Einstein metrics. But the point is that the conformal factor is not global on the manifold. The thing that makes it conformally Einstein, that's conformal scaling, has a singularity along a hypersurface. And in general, among the examples that arise in this context, they're definitely not globally conformally Einstein. So you can't, it's a rather general feature of if you can't have two Einstein metrics on a compact manifold that are conformally related unless even if one is only locally defined, unless the thing is conformally flat. That's I guess that is usually ascribed to Obata, but in fact it goes in the four-dimensional case. It kind of goes back to relativity. People doing relativity in the 1920s discovered this fact. Yeah, so I would still say that from a certain point of view, these are kind of still ho-hum examples of Bach flat manifolds. Anti-self-dual is very different from Einstein, but we know a lot about it. We know a lot about Einstein manifolds now. They're very familiar. Double Poincare-Einstein is there's not such a good theory, and the really outstanding questions are related to, this is a situation where for it to be really non-trivial would be like if the two sides are not mirror images of each other, at least conformally. So I think that these questions about uniqueness of fill-in are really very pertinent, and you're not going to know enough about, I don't think you can prove anything about the Yamabe constant being close enough to, I mean, you can apply your results, but it's the same area of geometric analysis which might really be the source of an answer. It'd be more interesting if there exist examples, but where that were really different. And what you can definitely show is that if you had something where, in this context, where the two sides were topologically different, I mean, there would be one side would have some blow-ups in it, and the other would not. So this might be a very interesting source of. So what I have no prejudice about which way this question should be answered. If there are examples that do not come from the known constructions, then those would be actually extremely interesting. The theory would then become more non-trivial, I think. But I would like to see the question settled either way, just to know what the answer is.
Okay, so let's thank the speaker again. And we resume the session with Professor Mantegazza, who will speak about the Riemannian Penrose inequality via nonlinear potential theory. Thank you very much.
Thank you. And thanks to the organizer for the kind invitation. It's always a pleasure to come back to Pisa in a way. And I'm going to speak about a possible new and possible more elementary than the existing one proof of the Riemannian Penrose inequality by means of the analysis of some p-harmonic function, so by means of nonlinear potential theories. And that will let me say a couple of words before starting, that this is a joint work with Virginia Agostiniani, Lorenzo Mazzieri in Trento, and Francesca Oronzio, which is our common PhD student. She got her PhD very recently. And let me also say that the main line, well, the main research line leading to this was initiated mainly by Virginia Agostiniani, Lorenzo Mazzieri, and then also with Francesca Oronzio, starting her PhD, and I got in the collaboration only recently. So the main contribution to all this are due to Delphi, and there is some smaller contribution due to me. And also another word is that I will say something sometimes about physics. Don't trust me too much, okay? I confess I'm quite ignorant, so I'm studying. But okay, don't ask me too much about physics. Okay, so what is the main characters here are these guys, which are asymptotically flat manifolds. So are smooth, connect, and complete Riemannian manifolds, with or without boundary. For the first half of the seminar, there will be no boundary. Then I will deal with the case with the boundary. In dimension at least 3, and they're called asymptotically flat if actually morally at infinity they get flat. They get flat in a controlled way. For instance, we are asking here that there are these ends. It can become flat in several directions. They are called these ends of the manifold, and on each of them, via diffeomorphism, the matrix becomes the Euclidean matrix plus a perturbation that actually goes to 0 at in some way, at some level. There's this order of decay of this perturbation of the matrix, and the order says that the metric, the first derivative and second derivative, goes to 0 with this asymptotic expansion. Examples, for instance, where you see that you have example with 2 ends, 3 ends, and single end. This is particularly important because actually, as you can imagine, represent morally some kind of black hole, actually, in the standard films or pictures of black holes. And in fact, this guy here, with a special matrix, which is this guy here, which is Rn minus a ball, and the metric, which is exactly this expression here, it is called the Schwarzschild manifold on mass M. It is a rotationally symmetric metric, so you can imagine Rn cut away a ball, and this matrix makes this guy to look like this, actually. Notice that the metric is conformal to the Euclidean matrix by this factor, which would be the Euclidean matrix, but there is this factor that goes to 0 at infinity. Exactly. This is one of the physics stuff. This is okay. Yeah. Let me see. Maybe I wrote something about it's no more working. I think the battery is gone. This. Okay. Maybe it's working. Okay, they are asymptotically flat in one hand and conformal, 0 scalar curvature. And I think I will say in a moment thanks for your remark. It is a space-like part of a real Schwarzschild metric, which is a 4 manifold with a Lorentzian metric on it that represent the real space-time. This is only one of the space-like hypersurfaces inside. Yeah, right. Okay, just a remark. The sphere x equals to m over 2 with this power is a totally geodesic hypersurfaces. If we are in dimension 3, this is a surface, totally geodesic, and some minimal hypersurface in the space. So there are some remarks. Well, we have two information: the topology. The information topology, you have topology, you can have a very complicated topology, but concentrated in a bounded set. And the second is the behavior of the metric in the large. So as I said, it's becoming flat at some point. Actually, this definition is not actually uniform in literature, since you can change the order of decay, the requirements on the decay of the metric. You can even ask more or less derivative to decay to zero at infinity. We ask it this since it is okay for our goal, actually. So control on the second, decay up to the second derivative, actually. And okay, this is possibly connected to what you said, that I expect that this guy arises space-like hypersurfaces of real space-times, satisfying the Einstein equation in the real space-time, in the Lorentz metric. And they actually, this idea that all the topologies concentrated here and very far you are close to Rn means more or less that you are modeling some isolated gravitational system, where everything is happening in a bounded region of space, or space-time. Okay, this guy have a geometric invariant for each end, even if I will concentrate on manifolds only a single ends, but in general, for each end of one of these guys, assuming that you have integrable or non-negative scalar curvature, actually, you can define the so-called ADM mass, which actually is defined at this not so nice limit. You take your chart that derive decay, as I said before, you compute this integral on large spheres of the chart. This guy here, this is more or less the Hausdorff, by the canonical measure that you get from the metric on your hypersurface on this sphere, larger spheres. There's a factor in front, and you send the radius of the sphere to infinity, and what you get you get this limit that actually, in our hypothesis, C2 control on the metric at infinity, it exists, and Bartnik and Krushel, they prove independently that this limit exists, is well defined, and does not depend on the coordinate chart you choose to describe your manifold at infinity. Okay, so what is, well, there are other ways to define this ADM mass as a limit. And anyway, all them have in common that they depend on the first derivative on these guys here, actually. For the Schwarzschild manifold that I described before, actually, the mass M coincide with the parameter M that I used here, which is actually the mass of the Schwarzschild manifold. And in a way, so here there is just a remark, there is a discussion on what is the mass of some space-time or space-like hypersurface space in a space-time. And okay, there were several proposals. Maybe you heard of Hawking mass or other definition of mass for an isolated gravitational system. Anyway, the fact that on the Schwarzschild manifold, this definition of mass coincide with the parameter M, it's a standard requirement. Sorry. Okay, in general, you can imagine, well, this is physics, so take care about that. This Schwarzschild manifold, this is something other guy, is a model for isolated gravitational system. The hysteria of non-moving spherical symmetric status stars or black holes of mass M, actually. And okay, this ADM mass come from the name of Hernowit, Deser, and Misner. They suggested represent the total mass of this isolated gravitational system. So they discovered that in this space-time, which are foliated by this space-like hypersurfaces, evolution of an initial hypersurface under equation related to the Einstein equation, this quantity is preserved in time. And they suggested it can represent the total mass of this isolated gravitational system. Okay, this is possibly the most important thing about this ADMS, the positive mass theorem. There was a conjecture then shown, and Yao proved it in '79. So you have a three-dimensional Riemannian manifold, complete, only one end, asymptotically flat, and you ask the scalar curvature is non-negative. And the conjecture and then a theorem is that the mass is larger or equal to 0. Notice that this is called the positive mass inequality, with equality only if you are on R3. So there is no curvature at all. And notice that I put R3 here. So the initial idea is that this theorem holds for every dimension, but actually, I think now the accepted proof is up to dimension 8, because, for instance, this proof of Schoen and Yao uses regularity of minimal surfaces that holds up to dimension 7, minimal hypersurface inside the manifold. So from now on, I will discuss only the three-dimensional case, and possibly only one end asymptotically flat manifolds. In a way, this theorem says if you interpret the curvature as some distributed local energy or mass, actually this theorem says, okay, if you locally your energy or mass is positive, it should be natural that the total mass is again positive. This guy here. Okay, as I said, from now on, I consider only three-dimensional case, and all the asymptotically flat manifolds have only one end. So they are morally very similar to the Schwarzschild guy. And this theorem has several proofs up to now, and with several approaches and tools used. The very first one was the one that was shown in Yao, using minimal surfaces. Then Witten prove it for not only three-dimensional case, but in general for spin manifolds. Lockamp used an argument based on non-existence theorems for positive scalar curvature metric. Wiskinen and Manning in 2001, and this is very interesting work because will be generalized to the situation with boundaries I'm going to speak about, use the weak version of inverse mean curvature flow. And more recently, Lee uses the Ricci flow with the idea of deforming the metric, transform the metric of your manifold to a flat one, and showing then during this transformation by means of Ricci flow, your ADM mass decrease. So since clearly the ADM mass of R3 is 0, if your mass decrease and whatever deformation you use to pass from the original manifold to R3, if your mass is decreasing during the deformation, clearly the initial mass was larger, so it's positive, not negative. Because as I said, 0 only if you are on R3. Even more recently, Bray, Casara, Curia, Stern uses in 2019, moving from another previous paper by Bray. They use the analysis, use harmonic function on the manifold and study their behavior in order to get the inequality. Okay, what is the Virginia Agostiniani, Lorenzo, Mazzieri, and so on? So they got a simple, in my opinion, more elementary, which means that you don't use too much tools from analysis, but actually the main tools you'll see will be the Quarta formula and Sard theorem. Since they found the monotonicity formula along several sets of appropriate harmonic functions, which are related to the minimal, as we'll see, to the minimal positive Green function with a pole. So there is they found a monotonicity that actually you'll see leads at the end to another proof of the positive mass theorem. The idea, well, first of all, there is a simplification by the very nice work of break as a curious term that I mentioned, actually it is sufficient to show by an approximation argument that the positive mass theorem work is true in the class of Riemannian manifolds satisfying the assumption that I mentioned before. Moreover, there is no topology. M is diffeomorphic to R3. So if you are able to do it without topology, you are able to do it even if you have a lot of topology concentrated in the boundary subset. And actually your metric is Schwarzschild metric, which is actually, as you can imagine, an enormous simplification of the problem. So you are passing from a very general asymptotically flat manifold to prove the theorem only in R3 with the Schwarzschild metric, at least on a large pole. So the idea is to consider this function here, which is an harmonic function, which is as a pole. Pole is G naught is a minimal positive Green function with pole at O for some point in your manifold. So you consider U, so you can imagine this function is something which goes to -infinity at some point and then grow up and becomes 1 at infinity. And consider this ugly at first sight function that they were very smart to find it, where H, you see this function varying from t from 0 to +infinity involve, it's an integral, wait, this is a linear term, and an integral on the level sets of this function here in this way. And H is the mean curvature of this level set, actually. Yeah. So you take this function, and what you see is that actually it is monotone increasing, which is absolutely not immediate to see, actually. Okay, at the very first, well, we have a function, we want to show that it is monotone while you compute derivative. And derivative, as you can imagine, is not completely easy to compute it because you are dealing with level sets which are moving. So you have to have some care, and level sets are not always smooth since the gradient can be 0 somewhere. So at the end, you compute your derivative, and actually what you find out that the expression is this almost everywhere, in particular on the regular level sets of your function. And what you see in this derivative, you see, okay, there is this constant here, which is clearly comes from differentiating this term, which is easy. That's the only easy. Then you have all this minus the scalar curvature of the level set, which is a surface. So you can recognize that here, this integral by Gauss-Bonnet theorem is only related to topology, because this is a surface, this is the scalar curvature, we coincide with the Gauss curvature. So you have Gauss-Bonnet theorem entering in dealing with this term here. And the rest, this guy what I call Q, it's positive. Positive because this is a square, this is a square. This is the trace-free part of the second fundamental form of the level set. This guy here is a square, and here you get R of the ambient space. And here where's the hypothesis on the scalar curvature of the ambient space gets in, because now all this guy is positive. So if I'm able to show that this sum of this 4 pi minus this integral is larger or equal to 0, I can throw this away and my derivative is positive, is non-negative actually. So since, well, it can also be proved that the function f is absolutely continuous, your derivative is almost everywhere non-negative, the function is monotone. What are the tools you use in doing this? Well, you have to be able to compute that derivative. You are level sets moving and then manipulating what you find out. And the two main tools are Quarta formula and Sard theorem. Sard theorem in order to exclude that we have too many bad level sets. Well, bad level sets or images, not too many critical values. But actually, harmonic function, we are dealing with harmonic function, are actually smooth. So the set of critical set is nice. Okay? And one can deal with the possible a priori jumps in the moving of your level set. If you have, for instance, an area where the gradient, an area with positive Lebesgue measure, but your gradient is 0, and you consider the level set can jump. But harmonic function have a nice level set. You have your Sartre theorem is available since they are smooth. So you can deal with these points where the gradient is actually 0, and you can deal with the even to the not regular level sets. This is clearly absolutely not true if your function is not smooth, and if your function is not harmonic or has something similar to be harmonic, clearly. So as I said, the positivity, the non-negative of the scalar curvature implies that all these guys is larger than 0, not larger or equal to 0. So you have this chain of implications. You have that. Remember, we have the previous simplification due to Bray and the colleagues that M is R3 and U are harmonic. You also have that every regular level set is connected and actually are spheres. Okay. And by the Gauss-Bonnet theorem, if you consider only the first two terms, you have this 4 pi minus the integral of the Gauss curvature. So this integral is always less than 2 pi, since it's a single by the connectedness surface. So this guy is greater or equal than 0. So what you get is exactly what you were saying, that you have the derivative is larger than 0. I say you can see that f is absolutely continuous, so f is monotone, non-decreasing. Okay, yeah. Well, actually, people use the inverse mean curvature flow, which is a lot less well-behaved than mean curvature flow, because we have h at the denominator. And so if you're not in a convex situation, you have points where h is 0. That's exactly the hard work that Wisken and Mann did in order to deal with this situation, to use the inverse mean curvature flow of hypersurfaces that also can be seen as a level set of some function. And this is connected to all these points of view. But we have to deal with the singularity in the equation. And that was exactly why they worked hard in their paper in order to do exactly what you said. And there is connection is there, but not with harmonic function, but actually morally with one harmonic function. So solution of, well, there is it's not direct connection, but solution of one Laplacian of u equal to 0, which is a quite ugly operator. I'll get back on that when I'm going to speak a little bit about Hillman and Wisken-Hillman proof. Okay, so we got the monotonicity. So actually, we have this function from 0 to plus infinity. So since we have a monotonicity, you see that the limit at plus infinity is larger than the limit at 0. The limit at 0 is actually 0. So the limit when your level set goes to the pole of the function. And the limit at infinity, miraculously, is exactly 8 pi the ADM mass, actually. Okay, how to get this? The limit in the right, it's quite easy, actually. It's a consequence of the asymptotic behavior of any green function when close to a pole, while the limit on the left-hand side is a consequence that we have a very precise description of the behavior of the metric at infinity. So when I go and compute that limit, I use as put instead of u this expansion at the right level, and what you find out that you recover the expression of the IDM mass that I wrote down before. What is this expansion? We have 1 minus this term, it's explicit. This is an eigenfunction on the sphere, and O2 here means the same as before, that after this term, the function u decay to 0 at infinity with the function first derivative, second derivative. Every derivative you have to add a unit here. So again, you have a C2 expansion, a control on the C2 decay of your function at infinity. And this is explicit since we know exactly how is the metric, and you can work out you know that U is harmonic, so we know a lot of things about harmonic function. In particular, we are able to find out this expansion. Okay, this clearly shows it's aligned to the positive mass theorem. Now we want to deal with the situation with boundary, which physically, again, the boundary, it's in a way the event horizon of some black hole inside. And Penrose stated the following inequality. So the same situation, but now you have a boundary. And again, scalar curvature is positive. And this boundary is the unique minimal surfaces in your manifold. Again, here there are several statements of this theorem. Okay, this is the one that we are able to prove. There are generalization of this that I'm going to get back in a while. So this assumption seems to be a little bit strong, but actually it's quite natural at the end. It is, well, this horizon that covers some black hole. Then in this case, the ideal mass is not only larger or equal than 0, but actually the Riemannian Penrose conjecture, and now a theorem, is that it's larger than the square root of the area of the surface, which is the boundary, divided by 16 pi. Okay, there are two proofs around. One is Wisken-Hillmanen, which is based exactly what we are saying, the inverse mean curvature flow, and as a byproduct is also gave a proof of the positive mass theorem if you don't have a boundary. And another of Bray, which is actually based on a conformal flow of the hermetics. It makes a conformal flow of the initial matrix, the matrix transform in a nice matrix, then is that where there is another monotonicity around, and at the end it gets the inequality. Well, if you want to try to follow the same level set line as we did before, well, actually you have to change your harmonic function and try to see if you find a good one to get the same result. Well, a natural choice will be to take an harmonic function in your manifold such that it goes to 1 to plus infinity. This time there is no pole around. You simply ask that on the boundary that your function is 0. So you have your harmonic function 0 on the boundary that goes up at asymptotically becomes 1. And again, you associate the analog of function f. Everything works in the same way. You get monotonicity, but when you go and compute the two limits, on one side you still get your 8 pi the mass on the limit when t goes to plus infinity, but on the other side you don't get what you like, which is this guy here connected to the area. What you get is exactly the capacity of your boundary, where the capacity for every exponent p is defined as the infimum of a gradient to the p for all the function that starts at 1 on this boundary. And actually, this guy here, unfortunately, is not larger than this one. Otherwise, we were done. So, one possibility, and inspired by some formal computation by Giorgi, that lead exactly to the line of Hillmanen and Wisken. Sorry, I miss a capital I here for Tom. We can look at the level set in this case of p harmonic function. So you instead of consider the standard Laplacian, you consider the p Laplacian, which is actually this operator here that I guess most of you know. For every p larger or equal than 1, a solution called a p harmonic function. So it's the same as before, but now instead of standard Laplacian, I have this guy here. And okay, I can ask myself if I can do something similar to what I did. Unfortunately, p harmonic function is not so nice like harmonic functions. P harmonic function, the best you can hope in general is that C1 alpha. It's a distributional solution actually here. And C1 alpha means, for instance, that you don't have SAR theorem. You need enough regularity in function to have available Serre theorem. But actually, suppose we forget about this. This function here, look at the operator. If you are far from the points where the gradient is 0, they are super smooth. They are perfect, like harmonic function. They behave more or less qualitatively like harmonic functions. All the mess is where the gradient is 0. So suppose we are in an interval or level sets where there are no critical points. So you can do everything without taking care of level sets which are not regular, and you can simply do your computation in a way very similar as before. Now the function f must be modified a little bit in order to make things go. You have still more or less the same integral. You change in a way, it's kind of reparameterization in time. So yeah, before we have 1 minus 1 over t. Here now we have to use this one as a level set, depending on t. You have to put these two constants here, this constant here and this square, which is defined in terms of the capacity. But at the end, this function fp is very similar to the previous one. Well, for p in the interval 1, 3, they're all the same. You are able, in this special case, no critical points around, compute the derivative, you get monotonicity, and at the end, you get the same. Now, you don't need to take the limit at 0 like before, because here you have your function is defined also at the very beginning, and which means that you are integrating on the boundary. The level set TP, if you put TP here, you get FP equal to 1, equal to 0, which is exactly U equal to 0 is the boundary of your manifold. So yeah, this is not a limit on the right, it's exactly a number. And okay, on the left side, you still get the same 8 pi for the mass. And on the right side, you have this not so nice at the first sight guy, which involves still the capacity. Like, remember, in the case 2, you get the capacity as I wrote before. And again, how to get this? Well, on the right side, it's easy because you know that h is equal to 0. You are working on the boundary, so you can compute easily this, well, compute easily, estimate easily this guy here and get this inequality. On the left side, again, you use an expansion for the p-harmonic function at infinity, which is actually contained in the work of Crucial. Don't forget about this red asterisk here. I'll be back in a moment. Okay, so the line is very similar. You have this expansion, you put in the same limit as before. And okay, this is what you get. We can call the P capacitary Riemannian Penrose inequality. But what is now the nice point is that now you have this way. Why don't we send P to 1? Actually, if we send P to 1 by previous work of Fogagnolo and Mazzeri, actually what you see that the P capacity in this very special situation that we have a minimal surface in this manifold converge exactly to the area. So if you send P to 1, it's easy to see that this guy goes to 1, this guy goes to square root of 4 pi, and this guy becomes square root of the area. Well, then it's easy. If you remember the inequality we were looking for, this means that 8 pi makes a dm larger than this guy here. And then putting the 8 pi on the right other side, you get Riemannian Penrose inequality. All this if you don't have critical points around. The monotonicity part was formal. I assume it's correct if you don't have critical points, but you cannot hope that because there can be. And actually, you absolutely need in this line Serre theorem. You need smoothness in order to have Serre theorem. And I said they are only the function only C1 alpha, not so smooth. Moreover, the set of critical points are not so nice like for harmonic function. There can be a lot of critical points, a lot of critical values. And actually, it's an open, very nice, interesting open problem to characterize the size of the set of critical points of a P harmonic function. I think the easiest conjecture that cannot have positive Lebesgue measure, but it's an open problem for some time actually. And actually, if you have a lot of critical points, they affect the regularity of too many level set surfaces, so making difficult to compute the derivative that we mentioned before. And also, we want that they are regular because at the end, we need that argument based on Gauss-Bonnet. And also, since we are not smooth enough, we are not harmonic function, the level set can even lose the connectedness during this evolution. And instead, you need, in order to apply the final argument that I mentioned before, you need one single surface connected and smooth enough to have a Gauss-Bonnet theorem to be applied. Okay, how to deal with this? But the idea is more or less following Di Benedetto in his work in existence and regularity, the best C1 alpha, as I said, of P harmonic function. So the idea of Di Benedetto is you have, remember, this was the P Laplacian operator. Now there is an epsilon, which means that you perturb the bad term, the term that can make the operator degenerate, with this guy here, with some epsilon, so becoming larger than epsilon. So this operator is no more degenerate. So it's strictly elliptic. So, and use it in stripes. So UP is the P harmonic function, the original P harmonic function, which is not so nice. You look only between two level sets, the level set 0, which is the boundary, and the level set UP equal to T. Inside here, solve this perturbed problem. And also in the work on Di Benedetto, what can you can find that, well, these functions are smooth. So you have SAR theorem now. And actually, they locally converge smoothly on every subset where the gradient of this UP is non-zero. And actually, if you consider a similar function, modified function, FP, with taking care of this epsilon that you put in the problem, this function pointwise converge often enough, not almost everywhere, but often enough for the conclusion. So to many level sets that form a sequence going to 0 to plus infinity. At the end, you don't want all the conclusion. You only want that when you get close to 0 and when you go close plus infinity, one is larger than the other. In a way, there is some kind of monotonicity, not on every level set, but at least on two sequences, one going to 0, one going to 0, the other going to plus infinity. And actually, well, what you lose is the monotonicity, since you are changing everything, but you lose with a controlled error. A controlled error which is going to 0 with epsilon. So you have an approximate monotonicity formula for this function. This function converges to the function that we are really interested in, which was the FP. You pass epsilon to 0 and you get rigorously, even in the general case, monotonicity of the function FP. And so, yeah. Big T here. This guy. I don't want to go up to here. I restrict. Yeah, I cut some at some point. Yes, I saw from 0. I always start with 0. Take a big T and solve this problem inside. No, then I send big T for a special sequence. That's more or less the idea of the often enough. That this big T, I get at least one sequence going to plus infinity. Okay, so you get monotonicity to FP. So the previous argument works. And what you get by the previous argument, sending P to 0. First get inequality for P, every P larger than 1, then send P to 0, and you recover the monotonicity, the Riemannian Penrose inequality by means of this result of Fogagnolo and Mazzieri. Some final remarks. The full statement or Riemannian Penrose inequality is that you have equality only if you are on Schwarzschild, rotationally symmetric Schwarzschild. And by this line, there are too many approximations. We are not able to recover inside this line the equality situation, actually. Second, comparison with the other proof. Our argument at the moment, but it seems quite difficult to be generalized, doesn't work if the boundary is not connected. You need a connected surface as a boundary. Instead, if in a way, if you have multiple connected components, we can think that horizon of multiple black holes. The same holds for the proof of Wisken-Hillman, but actually they allow non-connected boundaries. But what they conclude is that the ADM mass is larger than the square root of the area divided by 416 pi for each of the ones. In a way, their conclusion is if you have several connected component of your boundary, the ADM mass is larger than the square root with a constant of the largest of the surfaces. Instead, the brace proof actually get the most strongest statement, which is exactly the Riemannian Penrose inequality, even in the non-connected situation. So the total area, the ADM mass is larger than the square root of the total area of your boundary, even if it has 20 connected components. And now, just to be honest, my red asterisk about crucial expansion of the P-Laplacian function goes to plus infinity. Actually, we based it on the work of Crucial that studied this P-harmonic function at infinity, found out the expansion. He actually, in the paper, he did it only for very special pairs of dimension and exponent. For P equals 2, for instance, the harmonic case, it's okay. The expansion is there. And this also, and also said, okay, all the remaining cases, the general case, every dimension, every P, this expansion can be found along the same lines. Okay, we trust Crucial, but actually we are checking if actually the line of Crucial can be generalized to the general every dimension and every exponent. This expansion here can actually be worked out explicitly, since in the literature is not present. There is only in details only for some special cases, and Crucial says, okay, you can do in general following my line and so on. Actually, maybe it was a little bit too much confident, since changing in a way he uses the very good pair dimension exponent, and doing in general seems a little bit more complicated. We are checking that actually. It's not completely written down. And with this, I think I conclude and thank you for your attention.
Thank you very much. Are there questions or comments? Several.
So for P equal to 2, use the Gauss-Bonnet formula to get a sign for the monotonicity. So here,
In that point that I mentioned.
yes, here, where do you use that you are in 3 dimensions?
We are in 2 dimension.
Yes.
Always. Well, more or less, it appears a same term, extremely similar, more or less the same term, and you use simply the Gauss-Bonnet formula in the same way.
So
It's not very
is there a
detailed.
power of the Gaussian curvature that goes to 1 or?
No. It appears exactly the same term.
Oh,
with
exactly the same.
Exactly the
I
same.
see. Okay.
The derivative term in the P case has some extra terms, some coefficient around, but in particular, that term on the Gauss appears exactly the same.
I see. Okay, thanks.
The Q changes. The Q changes.
Were other questions?
What happened in higher dimensions? I guess you get other in the higher dimensions, you get the same variation.
You need Gauss-Bonnet.
Yeah.
For this line to work. So apparently it's not generalized, not possible to generalize this line.
Or perhaps you need the other type of curvature.
Possibly, yes. And but possibly you need some geometric topologic inequality like Gauss-Bonnet and something analog. Maybe in dimension, even dimension, maybe you can do something.
Okay. So are there other questions or comments? So if not, let's thank the speaker again. Thank you. Okay, shall we start with the last talk of this morning's session? Professor Gilles Carron will speak about geometry of a Cato's limit. Thank you.
Okay, thank you. So I want to thank the organizer for giving me the opportunity to talk here in this beautiful conference and also to attend to these nice meetings. So I'm going to report on a joint work and project with Ilaria Mondello from Paris 12 in Créteil and David Tevodros, who is now in Nantes and was before in Brussels. So recently, it appears that the Cato conditions that I will explain in a few minutes on Ricci curvature has been quite a useful tool in geometry. It seems that the first occurrence of these conditions appear in papers of Batugunezu and Palaria in 2015. So it was on purposes of characterize function with bounded variations on complete Riemannian manifolds with the help of the heat kernel. So let me give the Cato conditions. Okay, so I take is a complete Riemannian manifold. The Laplacians is the geometric Laplacian, so it is non-negative, so it starts by okay, so there is a minus, so that this operator is non-negative, and you can compare the Ricci curvature at each point with the metric. And I choose the functions, say rho, with a sign here, and I choose so at each point, so that rho is non-negative. So rho, if you want, is you take the lowest at each point. You take the lowest eigenvalues of the Ricci tensor, and if this lowest eigenvalue is non-negative, you choose rho to 0, and if it is non-positive, then you choose the opposite. It's only in order to work with positive functions that we introduce this minus. Okay, and so what is the Cato constant? Kt mg. So you run the heat flow for rho. Okay, so okay, then you get a function on time and space, and you integrate along time up to t. Then you get the single function on the manifolds, and you take the sup on x. Okay, so it's quite complicated expressions. So let me explain where does it come from. Okay, so the first thing is if it's easy to see that if Ricci is bounded from below by kappa, where kappa is a non-negative number, then you get Kt is less than kappa Kt. Okay, so you have So the importance is about how these functions go to zero when t goes to 1. Okay, so okay, K of t is like a kind of measure of the spectrum of a Schrödinger operator. So you look at your Schrödinger operator, Laplacian minus rho, and you look at the spectrum of these guys, but not on L2, in L infinity. Okay, so you take the it operator associated to these guys, and you look at the L infinity norms. And the answer is that this behave like 1 plus kt if kt is smaller than 1. So exactly you get this one. This is 1. So if this is small, okay. Okay, so it's kind of measure of the spectrum of this operator in L infinity. And it comes from the study of Schrödinger operator on the Euclidean setting, where these Kato conditions appear as an essential tool. Okay, so now let's go to geometry. What can So in a certain sense, the measure of this quantity is a kind of measurement of replacement of the conditions of the Ricci curvature to being bounded from below. So, and what is possible is to get geometric estimates under the assumptions that these you get a control on this Kato constant. So one of the results is the following. So you assume M is closed and kt is smaller than 1 over 16n. N is the dimensions. Okay. So the result is that for any point, any radius smaller than square root of t, you get a control on the ratio of the volumes of the ball of this radius over the volume Cn R over S. And here you get a strange power is E square n times the volume. Okay. It's kind of replacement, if you want. It's kind of Bishop-Gromov inequality. So Bishop-Gromov told you that if you have non-negative Ricci, then you get this inequality with Cn is n is 1 and E square n you replace by n. So a kind of weaker estimate that's the one you get from Bishop-Gromov. Okay, so this is something I shown some in 2019. Okay, and another result that I obtained. So this is A if you want. Theorem B. So it was been shown independently by myself and Christian Rose at the same time. So is that under these conditions, you are able to, and if d, excuse me, you take as time the diameter square. Okay, then in this case, the first Betti number. Okay, so this is the dimensions of the first is bounded by 1 plus some constant. And here you get to the power 1/3. So if it's smaller enough, then you know that the first Bethe number is smaller than n. Okay, so it's kind of replacement of the classical estimates by, so this is an analog of result by Bochner. So Bochner was in the case of non-negative and refined then by Gromov and Gallo. In fact, I can continue. It's possible to get plenty of estimates that you can get under lower bound on Ricci. You can get those estimates under these Kato conditions. Yeah, it's always for closed manifold, excuse me. Yeah. Yeah, this is the radius. This is this one. Yeah, a small error. Yeah, sorry. Okay, from these estimates and the result of Gromov, we know that we get pre-compactness results for the pointed Gromov-Hausdorff topology. This comes from the works of Gromov in the 80s, that if you get a sequence satisfying all that the KT are all that smaller than 1/16n, and you take a point and they are all closed, then up to a subsequence, you can assume that the associate metric spaces pointed converge for the point Gromov-Hausdorff topology to some complete metric space at some point. So what does it mean? It means that for every radius, the ball here, the ball B O alpha R, look like to the ball of the same radius in X. Okay, so you have a map here. You get epsilon alpha, a sequence of non-negative positive numbers that goes to 0. So that's this map is a good approximation of the geometry, meaning that for every point, this map, the distance are the same up to an error epsilon alpha. And the second condition is that your map is almost surjective. Any point in the image, you can find a point on the original ball that is mapped by phi alpha to a point nearby Z up to an error epsilon alpha. It means that if you discretize your limit at a certain size, it says epsilon. After a certain times, this, if you discretize also at the same size your sequence of manifolds, they look the same, the geometry looks the same at this pixelized size up to an error epsilon. Okay, and you get this for all R, and it's become better and better when you go when the alpha goes to plus infinity. Okay, so in the 80s, in the case where here in place of this you have lower bound on Ricci curvature, you have a wonderful works by Chigger and Coldings that gives some very precise and very useful information about the structure of those space. Okay, and that what we have done is recover the conclusions of the works of Chigger Coldings under this hypothesis on the Cato. Okay, so I'm now going to state a result. So what is our theorem? So what we assume? So we assume that you have a sequence. So we assume, so they are all closed. We assume that the Cato constant, we do not only assume that this Cato constant is small as some definitive time, we assume a way of decay to zero when t goes to zero. Okay, so we assume it is uniformly bound by some f that do not depend on alpha. And this is for all t between 0 and t. And the condition we put on f is that, say, f of t, for instance, is. And we assume that the integral, this strange integral, is finite. Okay, you take the square root of ft, you divide by t, and you assume it's integrable at 0, and f is increasing. Okay, so it implies that f goes to 0. So it implies in particular that this Cato constant goes uniformly to 0 when t goes to 0. And we took a point, and so a sequence of points, and we assume a non-collapsing hypothesis at this scale, so that this is scale invariant. Okay, and v do not depend on alpha. So it's kind of that the ball of certain radius, fixed radius, the volume do not collapse. And the conclusion, and we take x. So when we assume that this converge to x. So this is a hypothesis. And the conclusion is that the volume converge to the Hausdorff limit, to the Hausdorff dimension, Hausdorff measure. So if x alpha in m alpha converge to x in x, so with these approximate functions, then you get that the volume of every ball converge to the Hausdorff measure. It means that a priori, we only assume that the distance converge. This is something about the distance. It says that not only the distance converge, but also the measure converge. Now, it's the next statement is about the regularity. Here, the one that coincides with the Lebesgue measure on Rn. So that's it. On smooth manifold, this is the Riemannian measure. Exactly. And the second statement is something about the regularity. So you define the regular set in X as the point. So when you dilate the space, then the geometry look like the Euclidean one. So you assume that X, you divide by epsilon, you point at X, and you assume that when epsilon goes to 0, this goes to the Euclidean space with the Euclidean distance. Okay, in fact, at any point, you can extract third limit. So what I assume is that this limit is unique and is given by the Euclidean space. So if you're on those points on the limit, a point where you have a unique tangent cone, and this tangent cone is exactly the Euclidean space. And the conclusion is that the Hausdorff dimensions is less than n-2. And the fact that, so it's in particular, this is dense. Oh, excuse me, this is a complementary. Okay, so the complementary of this regular set is small. And you get, there is it's a regular, so that's me. And so the Hausdorff dimensions of the complementary, the singular set, is small, and moreover, there exists an open set U containing the regular set. So it's a dense open set that has the structure of a Hölder manifold. U is a Hölder manifold. So this result should not surprise those who know the result of Chigger Colding. They are exactly the result proven by Chigger and Colding. But our proof is different. Okay, so let me now comment on the hypothesis and so on. So why we have to assume that the manifolds are closed? So this is a technical point. So we do not assume any hypothesis on the diameter. It means that the limits could be non-compact. Okay, but once we can, so our hypotheses are invariant on the rescaling. So if you divide the metric by epsilon square, then the diameter becomes very large. They still satisfy your hypothesis, and then you can extract the limit. So you can, and in this case, the limit will be non-compact. Okay. So why do we have to assume the closeness? So it comes from a technical point of view that came from a work of Zhang and so work is inspired by so it's in work of they obtain a Liao type estimate under this kind of Kato assumptions. It was not done in this way. They really, in the paper, they make other assumptions, but really the technical point they need is the smallest on the Cato constant. So if you, it was transparent, almost the same proof work, so it was not surprising. And at some point, they have to use the maximum principle. So usually when you, how you prove such differential inequality, you differentiate twice, you get an expression, then you cook up a point where it's maximum, and then you need this point where the point is maximum. Okay, and so here, why you need the fact that the manifolds are closed. This is this point, precisely this point, so technical point. So and so it's good to. So what is so? Need a point where a certain quantity is maximum, and to prove Liao inequality. So, and it's certainly good to. So, what is so the main tool is this Liao estimate. Okay, so and where did it come from? So it comes from the Buchner formula. Okay, so I will not recall the Buchner formula, but the Buchner formula that it assumes that U solves the heat equations. So with my signs, then you want to have estimates on the gradient of U. And the result is that the gradient of U is a solution or sub-solutions okay, so in order to put your hand on some estimates on derivative of solutions of the heat kernel, you need some information about this operator, Laplacian minus rho. And the Cato condition precisely give you some estimates on the L infinity behavior of the associated semigroup, so that you get almost for free from the Cato conditions estimates on the gradient. Okay, and then yeah, it's you have to cook up more different, look at the derivative of log and so on to get estimates on the Liao. But this is this point. So it means that with the Cato condition, we have access to informations on heat kernel. We do not have access to informations on geodesics. Whereas the lower bound on Ricci gives you precisely this. You get controls on the behavior of the measure along geodesics, and this we don't have. So we need to follow a totally different argumentation than the one of Chigger-Collins. Okay. So and the second is about why do we need these conditions. So a first thing is to improve the exponent. Okay. We get a better Cn, so C depends on F. Here you get the power n. Okay, if R is bigger than S positive square root of t. Okay, so we are able to improve under only the fact that the Cato constant is small at some point. Then you get here an exponent, but it's e square times n, 10, for instance. And with this constant, we are able to, it's possible to improve to n. So it shows that under our hypothesis, the limit as necessary Hausdorff dimensions n. Okay, so this is the first. Okay, so perhaps I will erase the same blackboard. Okay. So let me now give the okay, so assumptions that implies that we get so clearly if you get Ricci bounded from below, okay, in this case you get uniformly, then you get okay, this function is fine and it satisfies your hypothesis. Okay, so another condition that has been discussed is this one. When you get the diameter square, you take this function rho, and you measure how far your function rho is bigger than k. Okay, like this, and here you have p. Okay, and here you take, and you assume this is something smaller than p and n, and p is something bigger than dimension over 2. So it comes from works of Gallo that under such a hypothesis you get the same results as the one you get on the geometric estimates, estimates on the Betti numbers, estimates on the volumes, Bishop-Gromov, and so on. Okay, and so under those conditions, so it's a result by Rose and Stallman. So in this case, you are able to show that f. So you assume this for all alpha, you get something like this. You get some constant p, n, and here you have something like this. So this is d square I get, and here you get some power, which is 1 minus. Okay, so you get that this function behave like t to some power, so it satisfies your hypothesis. Okay, and the third conditions that implies this. So assume that the scalar curvature is uniformly bounded, and that's the Q curvature. So this is something like Laplacian of the scalar curvature minus some positive constant Ricci squared plus another constant. And you assume this is bounded from below by kappa squared. So in this case, you get that f is, or any dimension, provided you assume. Yeah, you can use Q curvature, but you can use any combinations of those so that here you get a negative coefficient. Or if you have a positive, you assume the reverse inequality. So it's yeah. But so it's kind any if you have such global estimates, then it's fine. Okay, and bounded from below. And then you get something like this. So what is good? This is so you get something like this. Okay, so it's fine. You get exactly the conditions. Yeah. Sure. No, it's a scaling. Everything is scale invariant. So you can assume t is 1, for instance, and you scale the metrics. If you scale the metric by square root of t, then you get that you divide by square root of t, then you get all the estimate at time 1. So it's just a scaling factor. So it's all these things behave nicely if you scale the. So it's no. T is fixed. Do not depend on alpha. T is fixed. So if you want, it's meaning that if you assume that kt is smaller than some quantity, is somewhat equivalent. The hypothesis kt is smaller than 1/60n is something analogous to say that the curvature is bigger than minus a constant over t. Okay, so if you get this, okay, so assume this is smaller, then it means that the t for which it's small, meaning that you have a lower bound on Ricci. So it's a way of measuring how the Ricci curvature, the negative part of the Ricci curvature is big. So if it's small at certain time, it told you that you need Ricci has to be big enough so that it's okay. And something I show with Christian Rose is that assume that for all point and all radius, you get so you take the mean of this rho alpha. Okay, so if you scale well, here you have to multiply by r squared. And assume this is bigger than some constant. And here, where alpha is positive. So this scale invariant, and so you assume this goes uniformly to 0 with respect to r. In this case, you get a uniform control. Okay, with some power of t. Okay, it's kind of, if you want, it's kind of more norms on the Ricci. This kind of estimate. Yeah, no, it's a power, so it's a, let's say, theta. And theta is between positive and below 2. So if theta is 2, then you get Ricci curvature bounded from below. It's kind of more estimate on this function rho. So if you have a uniform more estimate, then our hypothesis is fine. Okay, so it's kind of so now let me, I will not explain the whole proof, but one crucial point. So a very important tool in the works of Chigger-Colding was the Bishop-Gromov inequality. So it's given as a monotone quantity, a ratio between the volumes of ball on your manifolds and the volumes of the balls in the models. That is monotone, and if it's almost constant, then you know the geometry. So you need first a monotone quantity. You really use a monotone quantity, and when this quantity is almost constant, then you understand very well the geometry. Okay, so in this setting, we need the crucial point. The first crucial point is to get such a monotone quantity. And what we did is we find a family of monotone quantity. So this is what I'm going to explain now. Okay. So take, this is a closed manifold, and I assume that KT is f of t. Okay, so f is a measure the size of the Ricci curvature, if you want. Okay, and I call h t x y the heat kernel of mg. Hein, donc recall on the Euclidean space the heat kernel. So this is the Schwarz kernel is given by the Gaussians. So it's 1 for pt. Okay. And what is known is kind of the Gaussian behavior of the heat kernel is something universal, something that is really, with very weak estimates, it's possible to get this Gaussian estimates. Okay, it's come from the work, for instance, of Gregorian. So we introduce u. So it's a function on time and on the manifold. Okay, that kind of replacement here. So we introduce that we decrete that these functions as the Euclidean behavior. And then there is a Gaussian term. And here we put utxy. Okay, so we introduce kind of fake distance, if you want. Okay, here. And the good point is when t goes to 0, u of t goes to the distance squared. Okay, this is called the Varadan formula. Okay, and now we cook with this function u some quantities that depend on two parameters, so point and parameter. So then we introduce theta x st. So we play the same role, but we say this is our distance, and we integrate the Gaussians so that this was the distance squared. And we integrate in y. Okay, so this is a point on the point on S and T. So, but yes. No. So now I draw a picture, perhaps. So here I have S, and here I have T. Okay. So here I have T is S. So when T is S, I integrate the heat kernel. Okay, so it's 1. So here. This is 1 here. You integrate the heat kernel. It's S here. It's for S equal T. This is the heat kernel. So you integrate the heat kernel, and you integrate the heat kernel, you get the solutions of the heat equation starting for 1. It's U. Every time is 1. Okay, now if T goes to 0, you are here. You go to exponential minus the distance. So you integrate the usual things. Okay, and now there is another parameter. So it's T over 4, T over 2, where after computations, you use the semi-group law. And you get XX, excuse me. Okay, so this is the Hut kernel on the diagonal multiplied by this quantity. So on the Euclidean space, this is 1. Okay, and when T goes to 0, this goes to 1. Okay, so here, this goes to 1. Here it's 1, and here it's also go to 1. So our result is that you get a curve like this that is tangent here, where if you go along these lines, the functional is monotone, but not on the same things. Here it's decreasing, here it's constant, and here is increasing. Okay, so the result is that, okay, the red regions, lambda T, okay, then you have to multiply by a certain constant. Here you multiply by, so going to, you have to multiply by some things is T over S, S minus T, and here you have exactly, you have exactly these quantities that appear. Okay, so if Ricci curvature is bounded from below, is non-negative, then you get that this quantity is monotone. So this is always and so it's non-increasing and non-decreasing. So it changes exactly when you cross the diagonal. Okay, so and for when you have Ricci, then you can, here you have 1. Okay, and in this case, here, this is Bishop-Gromov, and here, this is Liao. Liao estimates imply that this quantity is monotone increasing. And Bishop-Gromov is equivalent to this quantity to be decreasing. So it's kind of family interpolate between the two. Okay, all this monotone quantity. Why it is useful? Now, what purpose? So here, so what we show is that this monotone quantity, you can define them on the limit. But to define them on the limit, you need to add extra things. You need the measure to converge, and you need the Hut kernel to converge. Okay, but assume this is the case. Okay, assume you have measures that converge to a certain measure, and Hut kernel that converge to a certain Hut kernel. Then everything converge. You can use kind of adapt the Lebesgue convergence theorem to show that this quantity also converge. So on the limit on X, you get such a almost monotone quantities. And now on X, so you need a measure, you also need an operator, kind of Laplacians. Such quantities that are limit on the quantity, so they are also monotone. they're almost monotone if you multiply. And now you look at tangent space at your guys. Okay, if you delete here, so you get the same things, but if you delete, you get on the tangent space, you get that this quantity there will be constant. They will be constant along the line here. Because going to a tangent space, it's the same thing that because O's quantity has invariant by deletions, it means that the things you recover on tangent space are exactly the limit you get here, and they are well defined. So it means that on tangent space, that is limit, and you fix a point, say mu Laplacian, and you fix a point here. The functions theta x lambda t lambda s are constant. They are constant and they do not depend on the limit to choose because they live on your space. Okay, so you get a kind of rigidity. You get a kind of eight-kernel rigidity from this monotone quantity on the space. And now the hard work is to show that in fact you get rigidity. For instance, it implies that these tangent space are all tangent cones. That you get at most of the points you get that those tangent cones splits. And then with this, the usual arguments plus small details of what Chigger coding have done can be adapted. Okay, so that is I want to end now.
Thank you very much. Are there questions or comments?
Yeah. Yes, but it was no. This works. The regular set will be the point where these limits. So you take the point are all ones.
I see.
So if it is one, then your tangent space is. This is always.
Yeah. I see. But then.
But it can take different values, and.
Does this give new information on the singular set?
Yeah. It gives you that the a priori it will give you that with some work that singular set is Hausdorff measure 0. But we have also like I do not repeat all the result of Chigger codings, but we have also the stratifications and so on. So it's
this connection, or better, interpolation between Bishop-Gromov and Lee and Yao that you mentioned was already known, or it is contained in your paper?
I don't think so. But if you go in the non-negative, if you go to Bishop-Gromov, you translate what Liao tells you. It tells you that this function U satisfies certain inequalities, and it is exactly the quantity you want to have the good signs in order to the quantity to be monotone. So, but it's first steps. Okay, it was first to find such monotone quantity related to the heat kernel on manifold with non-negative Ricci, and because this was the only information we have, so we know this heat kernel. We do not have access to this one, and so the idea with this fake distance, there are a lot of results by, for instance, a paper by Kolding, where he introduced such a function that is related to the level set of the green functions, like the talk, your talk just before. And also, you have this Husken monotony formula for the mean curvature flow. So they are exactly related to another quantity that is exactly, you take the extrinsic heat kernels and you integrate. So it's there. So it's not, in certain ways, there are many occurrences of this kind of thing to try to cook up such a, but then, you have to make computation. And
there was another question there.
Referring to the codimension 4 conjecture, you have some guess of a condition that could replace an upper bound on Ricci that could come from spectral geometry. Even
we only have to assume that the same kind of results, but not with the lower bound on Ricci, but to take a full Ricci tensor.
Okay.
In this case, we get some codimension 4. But in this case, it's not, you have not to take the square root of f. You have to take another functions.
Thank you.
Another power.
Are there other questions? So if not, let's thank the speaker again. Thank you very much.
So, of course, it's a great pleasure to introduce you Tristan Rivière from ETH Zurich. He's going to talk to us on min-max hierarchies, minimizing vibrations and minimal surfaces. So, Tristan,
okay, thank you, Claudio. So I would like first to thank the organizers, so Giovanni Catino and Andrea Malchiodi, for this very nice invitation. It's always a great pleasure to be back in Pisa. And thanks also to the Center the Giorgi for the perfect organization. So thank you. So I'm going to speak about min-max. So that is variational techniques to capture critical points which are not necessarily minimizers, which have non-zero Morse index. And I'm going to present a strategy which is to produce min-max problems in an iterative way. So you produce a min-max problem, and then it generates another one, and so on and so forth. So this is what I would like to present. This is what I call min-max hierarchies, and I will apply it to several situations. Okay, so but before, in order to present these hierarchies, so I will take maybe the linear framework. So the easiest framework you could imagine, which is about computing, you see, the eigenvalues of the Laplace operator. We're going to do the Rayleigh quotient for the diagonalization of the Laplace-Beltrami on a compact manifold. And there, what you do first is you introduce a Hilbert sphere of functions u, which are in W12 on n, and which are normalized. So the integral of u square is equal to 1. So, and then you get the first eigenvalue by a simple minimization of the energy under this constraint that is on the sphere. And it satisfies this equation here. Here I have a positive Laplace-Beltrami operator. I might be using later on a negative Laplace operator. So I ask for flexibility. Then once you have the first eigenspace, so what do you do in order to get the second one, the second eigenspace? So what you do is that you work orthogonally to this space, and you do again a minimization on this Hilbert sphere, but orthogonally to the sum of the previous eigenspaces. Okay, so and you go and so on and so forth, and in that way you produce a whole spectrum of the Laplace operator. So they are satisfying then these equations. So now imagine that suddenly you are a victim of amnesia, and that you don't know what a scalar product is, which is the case when you go in a nonlinear framework, when you don't have this nice Hilbert structure of W12. And then how can you recover the spectrum of the Laplace operator? So that is, we don't want to use this operation here, the orthogonal operation, but nevertheless, we would like to still find a procedure to recover the spectrum. So let me propose you something. So here, you see, we have, first we had a minimization on the sphere. So we were getting U1. But U1 is not the only, on the Hilbert sphere, is not the only minimum. There is another one, which is minus U1. Okay. So now what you do is that you are trying to, within the sphere, imagine the sphere is here, you're trying to connect U1 and minus U1 with paths. So you do that. These paths, we will call them, and you will understand a bit later, sweep, for sweep out. So it's going to be a green path, which goes from U1 to minus U1. And of course, you try to make it optimal in the sense of, you try to minimize the maximal value of the Dirichlet energy within the path connecting U1 and minus U1. And you get this purple dot here, U2, which happens to be an eigenfunction for the second eigenvalue. Okay, so it's a min-max operation. You look for the minimization of the maximal value, so like a mountain path, between U1 and minus U1. And know how many U2 you have. You have as many U2s. These are these purple lines here. You have as many U2s as the intersection of the Hilbert sphere with the second eigenspace. So you have like a sphere which is of dimension n2 minus 1, where n2 is a dimension of the second eigenspace. And now the idea will be to, in order now to go to the next step, will be to use the whole family, which is here, the whole purple family, which is here, and to use the topology. So we have something which is, so here I'm writing S n2 minus 1, where n2 is a dimension of the second eigenspace. We have a sphere, and this sphere has a relatively simple topology, but nevertheless very useful topology that we are going to exploit in order to get access to the third eigenvalue. How do we do that? The way we do that is like this. Each of these vertical lines that you don't see, which are invisible, which should be this sweep, this green sweep I had before, corresponds to these optimal passes joining +1 and -1. Okay, and now the purple line here is just the sphere Sn2 minus 1. And you create in that way, you see a cylinder, and now you fill in the cylinder. There is a way to fill in the cylinder, and you look at the minimal, the infimum of the maximal value of the Dirichlet energy in the box, and you get the third eigenspace. And this operation, you can iterate it. So in that way, you see, each time you use the topology of the space of solutions for the previous problem to create a boundary data and to get a cylinder, you fill a cylinder and you try to fill a cylinder in an optimal way. That is, you minimize the maximal value of the Dirichlet energy within the cylinder. So this is what I call hierarchy, because you use the topology of the space of solutions from the previous problem to create a new min-max problem. So let me go now to a nonlinear framework, and I will try to choose relatively the simplest nonlinear framework one could choose in order to illustrate this strategy. So it will be a bit different, but I think you will see very quickly the analogy. So now the framework I'm using is, I'm taking an ellipsoid here, and I'm taking a generic ellipsoid in 3 dimensions. So e square over a square plus y square over b square plus z square over c square equal to 1. And I choose it in a generic way that is a, b, and c are all different to each other. So now, if I minimize the length, now I'm interested with the length. I could also take the Dirichlet energy of curves, so length of curves on the ellipsoid. So if I minimize the length, of course, the minimum is 0, it's just a point. So a point, you can see it as a very tiny loop like this. So I make it a bit large because so that you can see it, and you orient it. So it's almost like the North Pole here. And now what you do, so this is U1, in a sense, this is my first purple dot. And now you have the second purple dot, which is minus U1. So minus U1, this is a tiny loop, but with the opposite orientation, which is here. And now the question is that, what is my green line? What is a green line which is going to connect U1 and minus U1? So I propose here the following green line, which is called a sweep out. That is, you will connect this tiny loop here, almost the North Pole, and here the South Pole, with oriented loops in that way. And it's going to generate the H2 of your ellipsoid. And now you minimize the maximal length of this operation. Okay, so it's relatively standard. And this is a way, in a sense, that min-max problems have been produced by Birkhoff in 1918, 17, Birkhoff. So he has been introducing this kind of families of curves in order to find a geodesics on arbitrary two spheres. Good. So now this is the first slide that we have for the eigenvalue. So we have the U1, minus U1, and we have the purple dot. Now, this is the purple dot here. This is the first geodesic here in the middle. Now, how many geodesics like this you have? How many solutions? So unlike the eigenvalue situation that we had before, here, because I'm taking A different from B, and A different from C, and B different from C, since I'm taking this generic situation. So the only other geodesic of same length, and this is the one of shortest length, is the one with the opposite orientation. So now let me try to draw the situation. So N2, you see, N2 is equal to 1. N2 is equal to 1, and the topology we are going to use is, it's a big word, it's just S0. It's made of 2 points. So what are the 2 points? So the first point is this sweep out, like this, with this orientation. And the second one is just the sweep out with the opposite orientation. And now you are trying to connect the two. And you are trying to connect the two, and you are trying to do it in an optimal way to try to minimize the length between this. So you are going to have one family of sweep outs, and you are trying to minimize the maximal length. So this is a bit like this. So what you are going to do is that your sweep out, so all the way, at each time you have a sweep out, but you see that you toggle the original sweep out in order to connect this one with that one. Okay, so we go from here to here. And now you do it in an optimal way. And you see that by doing everything is algebraic, you can write it. By doing it in an optimal way, you get the next geodesic. Okay, so this is a step 2. It has a slightly larger length. Now you look for the third geodesic. How do you do that? So you see, in connecting this one on that one, we were toggling in that direction. Okay, and we were getting the geodesic oriented in that way. Now we could have chosen to toggle in the other direction. That is, you will have now a situation like this. So here we had a 2-dimensional box that we filled. So now we have like here, we had this situation where we had we were passing from this to that, and in the middle we were having this one, say, and now we are going to connect the same previous min-max problem. but where you get the geodesic with the opposite orientation. And now you have a box, which is now, as you can see, it is going to be three-dimensional. You fill in, you maximize the length, and you get the third geodesic. So you see, it's exactly like the diagonalization of our Laplacian during the first part of the talk. What we were doing was in a linear, we were doing some linear iteration in order to avoid the use of the scalar product, because we don't want to use the scalar product because we know that in the spaces we are going to consider, there is no scalar product anymore. Okay, so we are not going to work with Hilbert spaces anymore, unlike the Laplace-Beltrami diagonalization. So here already, we don't have the scalar product anymore. So in that way, you see, you produce one after the other min-max operations. And what I would like to present today is no applications of this idea of the hierarchy to attack questions such as the Willmore conjecture, or questions such as the minimization of the Hopf vibration for the three energy. And there could be also many, many questions that could be approached in that way. Okay, so let's move on. So let me take the next question, which is a question from harmonic map theory. So harmonic map, you see, we consider the space, we consider harmonic map from the three sphere into the two sphere. And we consider the space W12, S3 into S2. And in this space, you have the Dirichlet energy, which is here. And harmonic maps, they are the critical points of the Dirichlet energy under this constraint that you take value into S2. So in particular, they satisfy this equation, and you can observe that for the specialists that I jumped from the positive Laplace operator to the negative one. So thanks for your understanding. I try to be ecumenic because I know that there is analysis and geometry. So. Okay, so it's a negative Laplace, therefore I put a minus in front. Okay, so we are looking for critical point of this energy, which are not absolute minimizers, which have Morse index different from 0. But before, so we are going to develop this kind of strategy of iteration. That is, you see, each time you use the topology of the space of solution of the previous problem. Here, the topology was super simple. It was the S0, that is 2 points. We were joining the 2 points. We are doing a mountain pass. Okay, so for the Laplace-Beltrami diagonalization that we were doing before, we were using the topology of the sphere, which was given by the intersection of the Hilbert sphere with the eigenspace. Now here, we are going to do the same. So the first thing you can do with this is first to minimize. And this is completely trivial. You get 0 when you minimize the Dirichlet energy among all maps in W12, S3 into S2. You get constant maps. But you ask yourself, how many constant maps do I have? I have as many constant maps as points in S2. And S2 has some topology. So let's exploit this topology to produce a min-max operation. So this is the sweep 0. Sweep is referring to the sweep out that I had before. It's this min-max boxes that I was considering that I call sweep 0, sweep 1, sweep 2, and so on. So now this space of, we take, for instance, the pi3, the third homotopy group of S2. The third, not the second. I could have taken the second, but there is something a bit more tricky there. So let me take the third one. So now, what is the next step in the hierarchy? So the first step were constant maps. They were obviously index 0. So now let's look at the next step. So the next step consists in looking at map, which goes from B4, the closed B4, into W12, okay, S3 into S2. And what you require is that at the boundary of B4, the map is constant. It is taking a constant value, which is a point in S2. And you ask for this configuration, this family, if you want, to realize a non-zero class in the pi3 of S2, which is equal to Z. Okay, so the first statement that you can make about that is that it is non-empty. This family is non-empty. That is, you can fill the box. How can you fill the box? The box that we were working with before. So it's relatively straightforward. So what you do is you take the Möbius transformation of S3. These are here the conformal transformation of the three spheres. That is, you pick a point in B4, strictly inside B4. You have this map, and you know that when you approach, just to have a visualization of these transformations, when you approach the point A close to, when you make it getting close to the boundary, then it is like shrinking the whole sphere to one point. So in stereographic projection, it corresponds simply to the dilations. You see, so this is the inverse of the stereographic projections of the dilation. So you have this explicit formula. So now what you do is that you take an arbitrary map, C1 map, you see, from S3 into S2, and which has a Hopf degree, which is non-zero. What you do is that you compose U with phi A. And you can observe using Hölder inequality that the family has a uniformly bounded energy, and you can convince yourself easily that everything is smooth. The dependence with respect to A is smooth. So therefore, you fulfill this continuity hypothesis. Moreover, as we said, when A is going close to a point that we call B at the boundary, it is bringing all the sphere to the opposite point, minus B, you see? And your map is converging, and here this convergence has to be understood as a very weak convergence. I mean, it's a convergence in W12, it's a weak convergence, but we don't care. You see, for min-max, when you look at families, sometimes you can take extremely weak convergence joining one point to its neighbors. So that's here we have a weak convergence to I should say U of minus B. Sorry, there is a typo here. It should be U of minus B. And now you use the fact that you started with a map of degree non-zero, and therefore you will guarantee this condition here that this family here is going to be an element of our family here. This family, we call it canonical family for people familiar, and I will come back to that, to the proof of Marquez and Neves of the Willmore conjecture. It has some resonance that I'm going to explain later on. So this is a canonical family associated to U. And it's an element here. So now what you do is that you take any such element, you look at the Dirichlet energy, and you try to minimize the maximal value of the Dirichlet energy. And this is giving you what I call the second width in the hierarchy. And the first thing you check, and which is not very difficult to check, is to show that this second width is non-zero. That is, that you don't have a min-max problem, which is trivial. And why is it non-zero? Because it is due to the Poincaré inequality. It's relatively short argument. What you do is that, so this is Poincaré inequality. You see, you have this control of the oscillation here of U by the Dirichlet energy, and assuming that you have a family here where this is extremely small for every A. You see, so therefore the oscillation is very small. So which means that UA is always close. I mean, the average of UA is always close to UA in L2 norm. And in that way, it's relatively easy. You can prove that you construct an extension within the ball B4 of your non-zero degree map at the boundary, non-zero of degree map at the boundary, and it is a contradiction because a non-zero degree map is homotopically non-trivial. So it's impossible to fill in the ball B4 in that way. So therefore, this guy cannot be too small. Therefore, the width, what is called the width here, the value of the inf max is strictly positive. Okay, so now the question is about the realization of the second width. And the question is, does there exist a guy, a purple dot, as in the Rayleigh quotient, as in the the eigenvalue, the computations of the successive eigenvalues of the Laplace-Beltrami operator, or as a computation of the length of the successive geodesics on an ellipsoid. So the question is that, does there exist a map realizing this W2? So if it is achieved, our intuition is to say that, since we are doing a min max, so you do a conditional min, that is, you do a min, but for the whole family. And the family is 4-dimensional. So usually when you have such a configuration, what you expect is that the second derivative of your u will have as many negative directions as the number of parameters of your min-max family. So you expect the critical point, the guy sitting in your mountain pass, 4-dimensional mountain pass at the top, as Morse index 4. And you expect, of course, to be a critical point of the Dirichlet energy, to be an harmonic map. So what you have to know, it's a result by Hamed El-Soufi from 1995, is that if you start with a smooth non-constant map, and if you look at its canonical family, then the fact that the map is harmonic, it is the maximal value of the canonical family. You have exactly the same phenomenon for minimal surfaces in S3. When you have a minimal surface in S3, you apply this, we will come back to that after. You apply this deformation of S3, and then the minimal surface is at the top of your family in terms of area. No, and moreover, such every non-constant harmonic map must have an index at least 4. So then you can ask the question, can we characterize the harmonic maps of index 4? And the answer is yes. So this is something I proved in 2019, that if you have a smooth non-constant harmonic map with index 4, then it is an harmonic morphism. That is, you can describe it as a composition of an isometry of S3, isometry of R4, sorry, the Hopf vibration, and an holomorphic diffeomorphism of CP1. So this is now the suspect, the guy which is supposed to sit, the purple dot. This is our purple dot. This is a guy which is supposed to sit at the top of our configuration. So yes, H is the Hopf vibration. This is from the book of Penrose, the Hopf vibration. This is this formula that I don't like particularly because you don't see the whole symmetry of the object. These cylinders corresponds to the pre-image of the various flat circles on the sphere. And I'm going to refer to that later on. Yes. Sorry? Yes, I mean, yeah, or using quaternions, or there are so many. I think the one I prefer is this one. Is simply, Z1, Z2 assigns Z1, Z2, because you kind of it gives the intuition, the projective line, because it gives the intuition that the norm of the gradient is uniform, that you don't see in the previous picture. Yes, you are right. Yes. So now minimizing the free energy. So how is it related to a min-max problem? And you will see this is going to call upon the Willmore conjecture. So there is a conjecture I've made in '96 that this Hopf vibration that we just saw in the previous slide minimizes the free energy among smooth map from S3 into S2, which is non-homotopic to a constant. So it's known that if you look at the P energy for P strictly less than 3, the minimum is 0. And if P is larger or equal to 4, I managed to prove that this is a Hopf vibration. But there is still the range 3 and 4, which is not covered. And why is it related to the hierarchy and the min-max operation that I was suggesting before? Is that assume that you could prove that the previous width is realized by the Hopf vibration. So this is where we still have a question mark here. Then we know that from the result of Hamed El Soufi, that this guy is a maximal of our canonical family. It's 8 pi square, you see, and this is implying this conjecture. The reason is that if you have a map which is homotypically non-constant, you have the fact that the 3 energy to the 2/3 modulo this constant coincide with the 2 energy because of what we were saying. The gradient of this map is uniform, is constant. So therefore, Hölder inequality is optimal. And then you use this, this min-max characterization. Then you get, using no Hölder inequality, finally, that for every map which is non-constant, which is non-homotopic to a constant, the 3 energy of the Hopf vibration is controlled by the 3 energy of U. So this is still a conjecture. And now, so what remains to be proven? So what remains to be proven is that this second step in the hierarchy is really achieved. So by an index atmos 4 harmonic map. So what you can use is that you can use a smoothing strategy, because the problem is that if you look at the space W12 from S3 into S2, it's a very wild space. It is not even an Hilbert manifold, nothing. It doesn't have really the nice structure to which you would like to apply Palais deformation theory, Palais-Smell deformation theory in infinite dimension. So in order to rely on Palais-Smell deformation theory, what you can do is to do smoothing. So there is one smoothing available, which is a Ginzburg-Landau smoothing, which is you relax the fact that you take value into S2, you take value into R3, then the underlying space is an Hilbert space, and you can prove automatically that for this energy, it is Palais-Smell, so your min-max is realized. It's realized, you have an epsilon width, which is larger than the width you want to achieve. It is converging to it, and it is achieved by a solution to the Ginzburg-Landau equation. So there has been analysis, in particular by Fang Hualin and Changyu Wang, about this passage to the limit. And there is something I should say also, is that at the epsilon level, thanks to a classical result by Laser and Solimini, you know that the index is controlled by 4. And now you can pass weakly to the limit. You have a solution. So you are almost there. You think that you are going to prove your conjecture. The question is that, is U star smooth? So this is the main question. So if yes, so this is a master student of mine who is now a PhD student. She proved that if U star happens to be smooth, then the conjecture is true. But then there is a true analysis issue there to prove the smoothness of that guy that we achieved in this way. There is but Mathilde implemented the whole thing, and then assuming smoothness, then she proved the conjecture. There is, in parallel, there was a nice argument by Daniel Stern, which says that assuming that U star is stationary, that is, there is a critical point for variations in the domain, then the conjecture is also proved. So Daniel has a very nice argument there. Anyway, so this is where we are. And now I would like to make a link with the Willmore conjecture, because you will see that the parallel is striking. So I'm going to do, okay, I'm going to present a bit, I'm going to jump, and maybe now my talk has a bit more justification to take place in this conference, because now I'm going to speak about a curvature functional. Okay, so I'm speaking about Willmore. So you take a closed oriented surface, and you look at all possible immersion of this closed oriented two-dimensional space, which is a two-dimensional manifold, I should say, because it is. You look at all possible immersions, and you introduce the Willmore energy for maps into S3, which is this energy, which happens to be conformally invariant. And there is a result by Willmore, which is, yes, from 60 something, which is telling you that the infimum among all possible two-dimensional manifold here, oriented two-dimensional manifold of the Willmore energy among all possible immersions of any possible surfaces is 4 pi. Okay, so it was maybe known before by Chang and Lachoff. And 4 pi is exactly the Willmore energy of the two spheres, the geodesic two sphere, for which h is equal to 0, and you know the area of the two sphere is 4 pi. Okay, so Willmore in 1965 asked the following question. So assume now that the genus of the surface is not the genus of the sphere, is not 0. So what is the minimum? So he computed, he proved that the minimum among axially symmetric, tori with some axially symmetry in R3, when you project them stereographically into R3, is really achieved by some special torus, which was the middle torus of the picture from the book of Penrose that I showed you before, which is a so-called stereographic projection of the so-called Clifford torus. And he made the conjecture that, so this is a conjecture, that the infimum of W of phi should be the Willmore energy of such an object, and that should be the only one modulo the action of the Möbius transformation, because as I said, this functional is conformally invariant. And just one remark is that below the Willmore energy, you have the area. Okay, and you have to think about the area in order to make a link with the previous part of the talk. The area is a 2 energy. The Willmore is a 3 energy, because the 3 energy was also conformally invariant. Okay, and just one remark is that you had equality before for maps which have constant gradient. Here you have equality if and only if the mean curvature is 0. So if and only if you have a minimal surface. Okay, so now I'm coming to the proof of Marquez and Neves from 2011 of the previous conjecture. So fortunately, none of the authors is present. So because it's, I'm going to make such a reduction of their beautiful ideas in this slide that I feel a bit shame. So, but since it's not recorded and nobody is watching, so it's okay. No, but I will be extremely reductive in my presentation there. So how did they prove the conjecture that the minimum of the Willmore energy is 2 pi square is achieved by the Clifford torus, which happens to be a minimal surface? So what they do is that, we go back to this original inequality we had in the previous slide, that the area is controlled by the Willmore energy with equality if and only if the mean curvature is 0. And then what they do is that they introduce a 5-dimensional min-max problem on the area of surfaces. So with surfaces, you have to be very broad you have to be very tolerant and accept guys which are really, really non-regular, like, cycles, chains and things like this. So Z2 chains, in fact. So anyway, so they have a well-defined 5-dimensional min-max problem, which happens not to be trivial if you start with surfaces of non-zero genus, you produce a canonical family, which belongs to this this admissible set for this min-max problem. So what they proved is that the width of this min-max problem is strictly larger than 4 pi. And since it's a 5-dimensional min-max problem, then you see, they proved that this is achieved by a minimal surface, because we are looking at critical point of the area, with index less or equal than 5. Of course, here I am so much sketchy that I feel a bit embarrassed, but just to give the idea. And there is a result by Urbano, which says that if you look at every minimal surface in S3 with index less or equal than 5, it is either a sphere or a Clifford torus. the torus we saw in the previous slides. So it cannot be a sphere because of this strict inequality. It cannot be 2 times a sphere because 2 times a sphere would be 8 pi, and you know that the width is strictly less than 8 pi. So it must be the Clifford torus, and you prove the conjecture in that way. So you prove that. And there is also something that I was mentioning, the result by Antonio Ross, that says if you pick an embedding, then of a surface which is non-zero genus, then you create a canonical family to which belongs to the min-max problem. So therefore, you can compare. You see the Willmore energy and this canonical family, the maximal area is controlled by the Willmore energy of the initial immersion embedding you were considering. In that way, you prove that W of phi is always larger or equal than 2 pi square, and you have to work a bit more to show the equality case, to study the equality case. So now I would like to make, and this is more a slide for people from this area. I know there are specialists in the room. I would like to make a parallel between the Willmore conjecture and what I call, you see, the previous conjecture about, the minimization of the 3 energy is like a mapping version of the Willmore conjecture. So you have the Willmore energy, which is conformally invariant, the 3 energy for maps, so the Willmore energy for surfaces, the 3 energy for maps. You have the area for surfaces, you have the 2 energy for maps. One is dominating the other, one is dominating the other, one is conformally invariant, the other one is not. Then you have the notion of canonical family by Antonio Ross that Marquez and Neves used. I don't want to enter into it. It's a 5-dimensional family. It contains the deformation by the Möbius group of your surface, but it contains one more direction, which is relatively singular. And then you had this Antonio Ross theorem I was showing at the bottom of the last slide, which corresponds to the Ahmed El-Soufi result. And then you have the Urbano result, which corresponds to the result I got in 2019. That is a characterization. Urbano was characterizing minimal surfaces of low index, while I was characterizing harmonic map of low index. Okay, so now, when you see that, you wonder, question, can one make a proof of the Willmore conjecture in the framework I was presenting from the beginning, which is this iterative framework, this hierarchy? So is there a way to formulate it? Is there a way to understand, to pose a min-max problem in this framework of iteration? And why? Because in fact, my idea is to prove the Willmore conjecture in higher codimension, nothing less. Okay, it's a bit pretentious, but it's always nice to have goals in life. Okay, so then, though I'm speaking a bit to specialists, there was one main obstruction in the Marquez-Neves proof to go to higher codimension, which is this 5th direction in the canonical family, which, by the way, corresponds to the eigenvalue, the most negative eigenvalue, which corresponds to the moving of your surface according to the unit normal flow, or the gradient of the distance function, if you want. And I want it, the problem is that when you move a surface, in even a super nice surface, analytic, according to the gradient of the distance function, at some point you create, focal singularities, and you cannot avoid it. That is, you more or less you are forced to stay within the framework of, a big framework of cycles. You cannot consider immersions. And that's a big problem also because this operation is very much codimension dependent, because taking the gradient of the distance to this surface is working well in codimension 1, but in higher codimension, it does not work well. So I had a problem with this 5th direction. And I was thinking about that. And also with the idea of putting it in the framework of the min-max hierarchy constructions. So I came to a solution to that. I managed to get rid of this singular direction and to put everything in the framework of the hierarchy. So for that, I need the following slightly bigger object, which is when I consider an immersion of a two-dimensional surface into S3, you associate to this immersion, it's a Gauss unit vector, which is the unit normal vector, but tangent to S3 at the point where you are, you see, and it's tangent to S3, but it's orthogonal to your surface. So now, once you have this Gauss unit vector, you produce the Gauss map. So the Gauss map is a wedge of these two guys. That is, this is the oriented two plane tangent to your normal to your surface. So it's a map into G2R4, the Grassmann manifold of oriented two planes in R4. So which identifies to CP1 times CP1. Which is I don't want to insist on that, but it is Keller-Einstein, and but this is important. It plays a role after. So it has a natural Keller form, which is a sum of the two volume form here, and that is going to be extremely important in developments that I won't have time to explain. Anyway, so you look at this wedge. You can also look at the pair, which is a lift, which is simply phi and n together. These two guys, they are unit vectors, and they are orthogonal to each other. Okay, so they take value into V2R4, the Stiefel manifold. Okay, good. So there is some Liouville form, and it is Legendrian, in fact. So it's coming from this structure equation. And this is important, but I won't have time to develop that. Anyway, so why are we considering that? If you have a minimal immersion, this was observed by, discovered, I should say, by Lawson in 1970. If you take a minimal immersion, then the corresponding Gauss map is a branched minimal immersion. And now if you take the wedge, so this Gauss map, phi wedge n, it is a minimal immersion in G2R4, which is S2 times S2, which sits into S5 square root of 2. So the first one is a polar variety. Here, the second one is a bipolar surface. So this one is an immersion. This one is, if you have a genus non-zero, it is not an immersion. It has to be branched. And now you have the area of the Gauss map, which is here. And this is, the min-max is going to be about this area here. Now you can tell me, okay, you are going to do min-max with this area, but you know, are you going to get minimal surface? And the answer is that there are good chances, because there is a result by Castro Urbano from 2007, which says that if you have a Gauss map, and the mean curvature of this Gauss map, that is, you have a critical point of this functional here, then modulo, so there is some kind of action of S1 on phi and n, so which is locally constant. Modulo this action here, you have a surface which is minimal. So this action corresponds to push the surface along its unit normal direction at a unit speed. So therefore, it is really interesting to consider the critical points of this functional here. So kappa 1 and kappa 2 are the two principal curvatures of your immersion. So now, what is the first step in the hierarchy? So we construct now the hierarchy. So you consider this functional here. So this is a null Lagrangian, but it is important to have it. And what you can prove is that this null Lagrangian, which is nothing but the area of your Gauss map, plus the integral of a Gauss curvature, is controlled by 4W of phi, and equality if and only if kappa 1 is equal to kappa 2. Okay, which is the case for a minimal surface, because kappa 1 equal kappa 2 equals 0. And there is a result with my PhD student, Gérard Oriols, that we proved, is that the minimum of this energy is 16 pi, and the equality is achieved exactly if you are in S2 times S2, you have such a configuration, you are mapping an S2 in that way where R is a fixed isometry. And now you are coming back to this here in the hierarchy. You remember we use the topology of S0, which is a set made of 2 points. Before, for the diagonalization of the Laplace operator, we were using the topology of the unit sphere of the successive eigenspaces. Here, what this is telling us, so here you see you are at the bottom. You are minimizing. Okay, so this is the first step in the hierarchy, and you have to look at the space of solutions. The space of solutions is given by SO3. So now you are going to exploit the topology of SO3 to construct the next step in the hierarchy. Okay, and this is what you do. There is a min-max problem, no, which is the following. So you look at the space of immersions with controlled Betti number, and I think I should not show this slide because I mean it's early afternoon and you know it's not very nice. I agree. So what am I considering? I'm sending 4-dimensional complexes. I'm looking at the into the space of immersions. What I'm asking is that I'm asking that I am continuous here, but the Gauss map is continuous, but for a very, very weak topology, which is this peak F refers to the flat distance. So it's you don't need a very strong continuity. And at the boundary of, so you send this 4-dimensional simplex, at the boundary of it, you see, you realize a non-trivial element of the H3 of SO3. Okay, and this is a problem that is going to bring you to the Willmore conjecture. And there is a generalization of it in higher codimension. The natural generalization, but I have absolutely no time to go into that. So what can I say? I can say, first of all, this family is non-empty. The width is strictly larger than the minimum, 16 pi. And moreover, for every immersion where the genus is non-zero, then you are part of you can create a canonical family. So using again this Möbius transformation. And what remains to be done for proving the Willmore conjecture in that framework? So what remains to be done is, so if W1 of P is achieved by a minimal surface with Gauss index, so the question is to know whether it is achieved by a minimal surface with Gauss index less or equal than 4. So what remains to be done is the analysis. So the two previous theorems, they are in this archive paper that I still haven't submitted. This paper is since July 20 on archive. I'm still waiting for the referees not to have only all the geometric part, because the geometric part is complete, but to have also the analysis part available in order to have a full proof of the Willmore conjecture using this mapping approach. Now you can say there is, Tristan, there is a big problem there, because the Clifford-Torres in the Marquez-Neves approach had index 5, and here you are getting index less or equal than 4. And this is where everything now is converging in a nice way, because there is a beautiful result by Castro and Urbano from 2007, which is telling you that the index of the area, okay, is equal to the index for this area of Gauss map plus 1. So this is why there is a shift by 1 in the index, and that instead of having index 5, we expect to have index 4. Moreover, it is you have also this Urbano type of characterization exactly for this functional, for the area of the Gauss map. And as a final gift, you get rid of this nasty 5th direction that was really codimension 1 related. So you have only the nice directions for which you can, which allows to restrict to immersions. You don't need to have to introduce these Z2 cycles thanks to this approach. So now what remains to be done to solve the analysis question is to implement the viscosity method that we developed with Alessandro Pigatti for surfaces, with Alexis Michla for geodesics. Alexis is somewhere in the room. And here. And for surfaces, it's a series of 3 works with Alessandro Pigatti. Now we have to develop this method, which is a smoothing method, a bit like the Ginzburg-Landau smoothing that we had before, but which is different, which is more tricky in a sense. And this smoothing method, we have to adapt it to Lagrangian framework because I didn't mention, but what is very important is that you are minimizing you are looking at critical point of the area under Lagrangian constraint because Gauss maps are Lagrangian. And this is where you enter slowly in the scalar Einstein business. So, but I have absolutely no time to speak about that. Yes, so I thank you very much for your attention.
Are there any questions? Claude.
So when you look at harmonic maps from S3 to S2, then you can produce maps of higher degree by composing with, I guess, an arbitrary holomorphic map from CP1 to CP1, right?
That's right.
Do those have, are those known to have some special status with respect to?
Okay, yes, very good questions. So in fact, you can be more restrictive. You can, instead of saying, okay, my map has op degree D, if you compose with this map, then your op degree is going to be, so if you have a degree L, say it's going to be L to the square times D. So you could impose that. The problem is, and you have a min-max problem and you should solve it. The problem is that is not to have a repetition of the previous maps.
Yeah.
You see, so this is where there is a difficulty. Now, what I didn't mention is that what was the next step for this harmonic map framework? What is the next step in the hierarchy? So in order to understand the next step in the hierarchy, you look at the space of op vibrations, you see, which corresponds more or less to the space of holomorphic structures, flat, I mean, in R4. And so it should be CP1, I guess. So the next step in the hierarchy is to use the topology of CP1 to create a new min-max, and so on and so forth. And by the way, there is also, formally at least, there is also a next step in the Willmore. So what is the next surface coming after Willmore? So you use the space of Willmore surfaces, you see, and you look at what is the dimension of this space, and you anticipate. So you have this cylinder, this box I was showing you, and you anticipate the index. And if the calculations are right, I was discussing that with Nikos Kapouleas last week. I'm getting should be the index of the Lawson surface that he computed with a collaborator some time ago. So it seems that this minimax hierarchy, yes, is going to make you visit the Lawson surfaces, but I don't know. I mean, of course, it's a way beyond what I can do.
Are there other questions or comments?
Yeah, still about those maps from S3 to S2.
Yes.
So you mentioned this limiting construction via the Ginzburg-Landau U star, right?
Yeah, so you can use, it's always, yeah, you can smooth your min-max problem, look at a slightly a more coercive and well-posed problem for the Palais-Mel theory, and pass to the limit. So this is a problem, yes.
And yeah, I wanted to ask if that would be singular. So would a singularity carry an index or?
No, okay, so you cannot exclude singularities because in fact the problem is conformally invariant, and you could have the whole by the action of the Möbius group in the target. You could have the whole map concentrating on the geodesic, and this cannot be excluded because it's invisible with the two energy, with the min-max problem. So this should not exclude. So it's like there is a dichotomy, either concentration or no concentration. So in fact, the result of Mathilde Janoka is a bit more general. She says, okay, so either I do not concentrate, then conjecture is proved. Or I fully concentrate on a geodesic, then the conjecture is proved as well. You can prove it. The problem is in the middle. You can have an hybrid situation. We don't believe this is true. And there is very tricky. We don't know how to handle that, the middle situation, where you will be concentrating only on a part of a geodesic. Yes. And then you get some strange object. Should not be true. I agree with you, but you seem to be going as well in this direction that it should not be true, but we don't know how to prove it.
Thanks.
Any other question? Okay, so in that case, before thanking Tristan again, let's take a 5 minutes break so we can set up the technology or the scenography for the next talk. And so let's reconvene in 5 minutes. So thanks, Tristan. Okay, so let's start with the second talk. I'm very happy to have Ramiro Lafuente from the University of Queensland, Brisbane, talking to us about Einstein manifolds with symmetry. So all yours.
Yeah, thanks, Claudio, for the introduction, and many thanks to the organizers for inviting me. It's a great pleasure to be here. I hope I can follow this set of amazing talks. I'm quite embarrassed, I think, but yeah, I always feel at home in Italy, so I'm very happy to come. And it's been a great conference so far. So I'll be talking about Einstein manifolds with symmetry. Please let me know if my handwriting becomes too messy or too small. I know it's a bit far away from the blackboard. So let me explain. Well, by now we all know what Einstein manifold means, but in this talk, to me, I'll be working with a complete Riemannian manifold, satisfying the Einstein equation, which up to scaling, I can choose lambda to be 0 or plus minus 1. In this talk, I will work with a negative case. And the question is, what do I mean by symmetry? Well, symmetry will mean that there exists a connected Lie group G acting on my manifold, satisfying some conditions, namely the action is by isometries. This is the natural assumption in Riemannian geometry, of course. The second condition is a technical one, so you can ignore if you want, that the action is proper. I mean, having an isometric action allows you to think of the group G as a subgroup of the isometry group. And the action is proper means that this is a closed subgroup. So we're not losing too much generality. I can always close it. But this one is really an assumption. I'm going to be assuming that the orbit space with the quotient topology is compact. I will explain why we make this assumption. It's of course by no means necessary. There's lots of nice examples without this, but well, theorems have assumptions. This is what my advisor told me. So this is ours. Then I should give some examples. So let me begin with the simplest compact topological space, which is a point, right? So section 1, part 1 will be the homogeneous case. So by homogeneous, I mean that the quotient is just, so the action of G is transitive, okay? So we are also assuming that we're looking for Einstein homogeneous metrics. So the first natural examples that come to mind are, well, hyperbolic space, but more generally, irreducible symmetric spaces. Of course, they have to be of non-compact type so that they are negative Einstein. Yeah, these were studied in early 20th century by Carron, of course. And specific examples include the hyperbolic space, complex hyperbolic space. For instance, one can look at determinant one matrices mod orthogonal ones of determinant one. That's another nice symmetric space. These are all Einstein homogeneous. Now you may ask, are they all symmetric? Well, the answer is no. There's plenty of examples which are non-symmetric. Perhaps the first ones that were found were these so-called Einstein solved manifolds. So these are simply connected solvable Lie groups. Now, if you don't like Lie theory or algebra, this word might be scary, but just think of a group that's a group of upper triangular matrices or a subgroup thereof. I'm happy with that definition for the talk. Simply connected solvable Lie group. And the metric is left invariant. So it's a homogeneous space and Einstein. And perhaps the first example of this type was found by Alexievsky in the 70s, because he was looking for quaternionic Kähler manifolds which are not symmetric in the spirit of Berger's classification of holonomy groups. And turns out that the first known symmetric examples were, so the quaternionic Kähler condition implies Einstein, and he found these homogeneous examples. I think in the positive case, we don't know, right? If there are no symmetric examples. That's a long-standing open question. In this paper, he also conjectured the following. That any Einstein negative, okay, homogeneous manifold must be diffeomorphic to a Euclidean space. So this is indeed the case for solvable Lie groups. One can prove by induction that a simply connected solvable Lie group, such as the group of upper triangular matrices with positive diagonal, is diffeomorphic to a Euclidean space. So there's no topology, right? Of course, the metric is far from Euclidean, right? It's negative Einstein. But he conjectured this is always the case for negative homogeneous Einstein manifolds. So the main result I want to discuss today is joint work, forgot to say, with Christoph Bohm from Münster. We proved last year that the conjecture holds. So any homogeneous Einstein metric with negative Einstein constant connected, well, it has to be connected, otherwise it's not going to be diffeomorphic to Euclidean space. And moreover, this is not really the core part, but one can deduce from the proof that M is isometric to an Einstein solved manifold. Now, I don't mean that this is at all related with a special holonomy, right? So there are plenty of Einstein solved manifolds that have nothing to do with quaternionic Kähler, such as, to avoid any confusion. but the difference between this statement and this one is not a lot. So the key theorem is that it's diffeomorphic to a Euclidean space. So are there any questions about the statement or? We have it as a corollary that any locally homogeneous compact Einstein manifold with negative constant must be locally symmetric, because these do not admit finite volume quotients unless they are, symmetric spaces. So in particular, yeah, that follows. Okay, so maybe I try to move this up. And let me start, before I motivate the next result, let me start with explaining the strategy for proving the conjecture. So now I changed notation for my group, sorry. It's well known that homogeneous Riemannian manifold can be written as a homogeneous space, namely a quotient of a Lie group acting transitively by the stabilizer at some point. Stabilizer is a compact subgroup. And now a fact in Lie theory, very useful, is that there exists a maximal compact Lie subgroup K containing H. And why do I consider this? Because I want to study the topology of M. And what's the topology of homogeneous spaces is well understood. I mean, it's not, I don't understand it, but it's concentrated in the compact parts. Let me put it like that. And so what happens is that the homogeneous space F mod H is at least homotopy equivalent to K mod H, which is a compact homogeneous space. So if the conjecture were true, right, the diffeomorphic to Rn, then of course H must be equal to K, because Rn is contractible. Now, the converse is not hard to see, and I know almost no topology, so this, if I can prove this, you can as well. The converse is also true, right? So you have to prove that the isotropy subgroup is the maximal compact. For instance, this is the case in symmetric spaces, right? The SOM is the maximal compact subgroup of the group of determinant one matrices. Okay, so how does one approach the question? Well, we're dealing with the Einstein equation, of course. This is a second order nonlinear PDE, extremely complicated. And now in the homogeneous case, this second order PDE becomes something a bit more simple, namely, it's an algebraic equation, or more precisely, a system of polynomial equations for an inner product on the Lie algebra, essentially. Okay. Now you might think, then it's very easy. You put it on the computer, you check, well, this doesn't work. I mean, up to dimension 4, 5, maybe it works. Then it's just too many. I mean, algebraic equations are not so easy to solve, right? Otherwise, the algebraic geometers will be out of a job. No. So this is an analysis conference in part. So PDEs are of course hard, but sometimes algebraic equations are hard. So we need to use a geometry to say something. And let me just summarize. So of course, the coefficients of this polynomial will depend on the Lie bracket of the Lie algebra of my group F. But in the case F is semi-simple, I don't want to write down this equation. You can find it. It's not very interesting to see it explicitly. The system of n squared and choose two equations. But in the case F is semi-simple, we have very poor understanding of this system. And by this, I mean, even in the case where F is SL2C, which is a 6-dimensional real Lie group, the conjecture was open, right? So 6x6 matrices, just algebraic equation, but we didn't know. So because the group is semi-simple, we don't know anything other than just brute force to check whether this holds or not. Now, in the case with F is solvable, we do have some better understanding, especially in the last 20, 25 years, mainly due to the work of Heber in his habilitation in 98, and later by Laurette, well, and many other people. I'm just quoting to me what are the two main results. They do study this equation in the case where the F is solvable. Of course, we're not interested in that case, because if F is solvable, then this is Euclidean space. So we want to study this case. Now, any Lie group can be like a mixture of solvable and semi-simple. Let's ignore that. This is the case we are most interested in for the conjecture, because semi-simple groups, they have topology, but somehow the conjecture says they should not have topology if they admit an Einstein metric. So namely, perhaps a simple case to have in mind is assume that the manifold is just a semi-simple Lie group. Let me put it even more specifically, SL3R. So an 8-dimensional Lie group of 3x3 determinant 1 matrices. And I'm assuming that this is the manifold. So namely, there's no stabilizer subgroup. And now the conjecture, we should be able to prove that there exists no left invariant Einstein metric. So no solution to this equation in this case. The reason is that this is not contractible. It has it's actually diffeomorphic to R5 cross SO3 or RP3 if you want no Lie groups. So what's the main idea? If you see this, right? Poor understanding of the algebraic equations, and then very good understanding in the solvable case, but it's not interesting for us. So the key idea is that, well, you might want to get rid of the algebraic power of homogeneity and maybe use less than homogeneity. So idea. But this is, of course, a very expensive price to pay, because you go from an algebraic equation to back to a PDE. But maybe it helps. So use less symmetry. So this was our main idea, I would say. And more specifically, what do I mean by use less symmetry? Well, you're studying this equation for a left invariant metric on a Lie group, right? In this case, SL3R, right? Now, I'm gonna decompose SL3R. Everything I say in this specific case can be done in general with more fancy words in Lie theory. Now, you can write any matrix as a rotation times something which is upper triangular. With positive diagonal, okay? So this group is the group of upper triangular matrices is solvable, right? And now instead of looking at the Einstein equation under SL3R symmetry, I'm gonna look at symmetry by G, right? So I look at the G action on M. Now the quotient is going to be SO3, of course. There's no intersection between these two factors. And the hope is that by looking at the Einstein equation in this setup with only a 5-dimensional group of symmetries, we can say more by the fact that this is a solvable group, and somehow the solvable part of the Einstein equation we understand a bit better. Okay, so this brings us to the next topic, which is and now somehow we change gears and we forget about homogeneous spaces. So the second part of my talk is called Einstein principal bundles. Now, I should have said at the beginning that, yes, maybe I forgot, but in this, our manifolds are non-compact because of Bogner's theorem mentioned this morning. A negatively curved compact Riemannian manifold cannot have non-trivial Killing fields, right? So we are going to be looking at principal bundles with a non-compact group. Freely, this is a free action of G by isometries, and then this gives rise to, this is a smooth closed manifold, and this is a principal G bundle. Okay, now in the Riemannian setting, if I have a metric G on M, then I can cook up a unique metric downstairs. I'm gonna call it G check, so that this map pi is a Riemannian submersion. Okay. Yeah, let's say for the semi-simple case, yes, I always choose the maximal solvable, so to speak. So yes. I want all the topology to be contained in the base somehow. And so I have a principal G bundle. And then, I mean, what's the picture? Well, you have a bunch, so G is a non-compact Lie group, right? So I have a bunch of G orbits. This is a G orbit. This is M, right? It's foliated by G orbits. G is non-compact, but the quotient is some closed manifold with some topology, maybe. Okay, so this is important. So we are studying the Einstein equation on non-compact manifolds, but where the non-compactness comes from a group action. Okay, so we want to be able to use maximum principle and other techniques in PDEs, but we allow non-compact and we control that with the symmetry. So I have to say a few words about the Riemannian submersion. So when you have a Riemannian submersion, there's the tangent bundle decomposes as, this is pi, right? So if you look at the kernel of the pi, this is the distribution tangent to the orbits, which I will call the vertical distribution. And then because you have a metric, you can take the orthogonal complement of this distribution. And this is so-called the horizontal distribution. So this is supposed to be a calligraphic H, right? And now giving a metric, a G invariant metric on M can be encoded into some data. So a G invariant metric on M, we can encode with the following data, namely, I need a family of invariant metrics on the orbit. I need a so this family of metric I will call GB. So this is parameterized by the base. It's a family. Because these are invariant, it's enough to consider scalar products on the Lie algebra of G. Now, I need to tell you this is a composition because V comes from pi, right? But the metric gives me H. So if I want to recover the metric, I need to tell you what's the horizontal decomposition. So that's H, right? So this in technical language of principal bundles, this is called the principal connection. And there's no confusion because connections in the Levi-Civita and all those that you know, they are of this type actually. You are willing to look into Kobayashi no Mizu. Now this gives me, of course, the decomposition B plus H. And I need to tell you the metric on B, on the base. So this data becomes the following, right? So notice that this family can be viewed as G hat, the metric on the fibers, is actually a map from B to, so scalar products, after I fix the background inner product, they can be thought of as, you know, general linear group modulo the orthogonal group. Right? And if I fix the determinant, I can actually consider a symmetric space, a nicer symmetric space, but let's ignore that. So, okay, so I'm almost ready to state ours. No, they are not. They're not. They are all G, diffeomorphic to G, as in any principal bond. There's no canonical diffeomorphism. You have to choose a point. But the metrics, I mean, here, no, nothing. They are not totally geodesic. The horizontal distribution is not integrable. The fibers are not diffeomorphic to isometric to each other. A priori, this is any family of scalar product which is smooth will give you a metric, right? Any principal connection and any metric downstairs. It's very easy to see that these are equivalent. Now, unfortunately, our second main result needs a bit more notation because we cannot quite prove that under these conditions. Now, of course, we're going to be studying the Einstein equation for G invariant matrix G. And the main result is that we have structure for this equation, for these solutions. But to do that, I need to introduce a subgroup, which is called the nil radical of my group G. So G is arbitrary still. But in the example, N is a maximal normal connected nilpotent subgroup, but you're not going to remember all those words. In the example, N is the subgroup of strictly upper triangular invertible matrices, right? Which is isomorphic to the Heisenberg group. So nilpotent three-dimensional Lie group, okay? So just think N is this is dimension 6. This is a subgroup of dimension 3, which is nilpotent. Somehow nilpotent is better. Don't ask me why. But theorem B, also in collaboration with Christoph Böhm, is about structure of solutions. So let G be a G invariant solution to the Einstein equation with negative Einstein constant. And let me assume that I'm in the principal bundle setup, right? So this is compact. Then, I mean, I have a subgroup here, right? So because we have a subgroup, we can look at the principal bundle under the N action. Why not? It's a subgroup, so it also acts freely, and it gives me a principal bundle. It's even less symmetry, right? But somehow the fact that N is, I lose compactness. This is bad, but it's the right thing to do. Satisfies the following. So firstly, this distribution H, the orthogonal complement to the vertical distribution, is integrable. Okay. In the language of principal bundles, it's the same as saying that this connection is flat. So the Einstein equation forces this very nice fact. Even better, the in orbits, now coming back to your question, they are all pairwise isometric, but only at these points. They are Ricci solitons. And of course, they are homogeneous Ricci solitons because the orbits are homogeneous spaces. The metric is invariant, okay? And it's well known that these are unique up to scaling. So in fact, the n orbits are all pairwise isometric and Ricci solitons. And thirdly, also to connect with the previous talk, this map that I draw there, G hat. So the family of metrics on the orbits, when viewed as a map from B to GLG mod OG, is a harmonic map. Okay, and this is almost a manifold of negative curvature. So this is closed, right? So it makes sense to talk about the harmonic map equation. And somehow the Einstein equation also forces this third rigidity, right? So this is our main result. Now, I'm not gonna explain how this works, but somehow this is enough. After you have to work hard, but theorem B implies theorem A. Now you know so much, but you still need to work. There's a lot of algebra involved, but the fact that you know all this much allows you to get a contradiction if you are in this case. Okay. Perhaps it's a bit more interesting to say how. What time did I start? Did I start 5 minutes past or? Okay, 6 past. So maybe I will focus on explaining the geometric ingredients for proving theorem B. I think it's more interesting for this audience. Are there any questions about the statement? No, I mean, in this case, unfortunately, this is not compact anymore because this is like, I mean, there's a bundle like this where the fibers are G mod n, and G mod n is like R3. So all the compactness, yeah, I lost the compactness of the base, unfortunately. But again, the non-compactness of this guy comes from a group action, namely the quotient of G by n. So it's still manageable. That's the philosophy, okay? That the non-compactness comes from symmetries. You should be able to do something and then integrate downstairs or use the maximum principle or something. Because they are all, no, it's not going to be constant. This there's a gauge group, so they're going to be isometric, but the automorphism of oh, sorry, this is not the Lie algebra G. This should be the Lie algebra of the n. The automorphism group of this Lie algebra acts as a gauge group there, so the map doesn't have to be constant, but they are pairwise isometric. Okay. Yeah, so with so to prove this of theorem B, you need to remember that O'Neill's formulas allow you to write the curvature of G in terms of the curvature of the curvature of this, the family of metrics on the fibers. You need the curvature of the metric on the base, and then you need two tensors, which O'Neill called A and T. These are the fundamental tensors of the Riemannian submersion. A is the curvature of the principal connection, essentially, and T is the second fundamental form of the orbits. So we want to prove that this tensor is 0. The A tensor is 0. And let me also introduce H. Now, this is not the horizontal distribution. This is the mean curvature vector of the orbit. So it's some trace of the second fundamental form. The orbits have higher codimension, of course, but there is a mean curvature vector anyway. And in the case of a principal bundle, you can write this as minus the gradient of the logarithm of, is this correct? Square root, yes. Square root of the determinant of Gij, okay? So for the sake of concreteness, if I take Killing vector fields spanning the vertical distribution, then I can define, I don't need to work on coordinates or anything. I can define this to be just the metric in this frame of Killing fields. And then by this very nice computation, I take the gradient, and this is the mean curvature vector of the orbit. Somehow this plays a role. You're gonna see in a minute. Then the equation you want to study, I'm not gonna write it down. It's in coordinates. It will take me the remaining of the talk, but I give you an idea of what's the equation, right? So the Einstein equation under, n invariance or G, I mean, on any principal bundle is going to be equivalent to 3 equations. Namely, there's going to be, Ricci is, you can think of it as an endomorphism of the tangent bundle, and there's a vertical and a horizontal part. So there will be like a vertical part, horizontal, and then vertical, horizontal. And well, this is symmetric, right? So it's gonna be the same. So the Einstein equation has 3 parts essentially. The vertical part is something of the form harmonic map equation for G hat, not the equation, but the left-hand side, so to speak, plus Ricci-Soliton equation for G hat, plus norm of A squared. And this is literally like that, okay? Is the harmonic map equation, the terms that are equal to 0 in the equation, plus the terms that are equal to 0 in the Ricci-Soliton equation, plus the norm of the curvature square. And then the second equation, this is a mixed one, vertical, horizontal. Now this is something resembling the Yang-Mills equation for the connection H. It's not quite the Yang-Mills connection, it's more complicated, but as soon as A is 0, this one disappears. And the bottom one is really complicated, but let me say that it's like a Ricci-Soliton equation for the metric downstairs, but there's a lot of terms that are not in the Ricci-Soliton equation, so it's somehow that's the flavor of the equation. And well, you want to use this and try to deduce all these properties, right? But you can see how, by looking at this one, if you are able to show that 2 of them disappear, then the other one will disappear immediately, right? So the idea is to try to cook up a nice function, a nice invariant function, and use the maximum principle on the compact quotient, okay? Yeah. Well, the metric G hat is a restriction of G to the orbits, okay? And G is invariant by the group action. The group acts by ambient isometries. It preserves this submanifold. So therefore, the submanifold is also invariant by these isometries. Is it? Take one isometry that preserves a submanifold. Then I claim it's also an isometry of the metric restricted to the submanifold. Okay, so then the orbits are homogeneous spaces. In this case, they are even, left invariant metrics because I'm assuming that the action is free. But yes. The vector field? No, I don't want to tell you, but there is a vector field. there exists X. It's not gradient. It's not gradient. Non-gradient, but there is a vector field. Good question, though. But no. So I mean, I should perhaps in 5 minutes mention previous work on this equation, not in a negative case, but related equations like Ricci flat under symmetries with compact quotient, right? So there's early work by Xiaoxun, sorry, Wrong in 98, paper in Duke. He actually studies not the equation, but the negative Ricci curvatures when G is equal to N is abelian in the context of some non-collapsing result. Because I mean, symmetries, I should have said, right? But they arise naturally when you look at the collapsing Riemannian manifolds with bounded curvature, right? So it's somehow not so unnatural to look at these assumptions, the symmetry assumptions. And they appear when you study the closure of the set of Riemannian manifolds with bounded curvature, right? Sometimes you're lucky and you have non-collapsing and then things are fine. But when you have collapsing in dimension, then if you have bounded curvature, the collapsing is due to some, this is a deep theory by Chigger, Fukaya, and Gromov, is due to symmetries, essentially, nilpotent symmetries. So then there's previous work by Neighbor and Tian, the context of a Gromov almost flat manifold for the Ricci curvature. They study Rich zero, nilpotent case. And then there's work by Lot, 2020, also the Ricci flat in the context of almost Ricci flat metrics. Here, G is abelian, right? So in our case, G is not equal to N and G is arbitrary, unfortunately. But they all use the same strategy, which unfortunately we only discovered after finishing writing up our paper. But in our strategy is actually similar. So they look at the function f, which is the logarithm of this volume element. I mean, not the volume element, the volume density, sorry. And they prove that, which is a G invariant function for them, right? It's G invariant. And then they look at Laplacian f for continuity with the previous talk. This is the negative Laplacian. But then there's a first order term. This is greater than or equal to 0. Now, because the function is G invariant, you go to the quotient and you apply the maximum principle and you get rigidity here, and then they can deduce contradictions or other things, right? So this will be our strategy. We need to cook up a function, find the PDE inequality actually. And in the inequality, we want to use the Einstein equation, throwing away the right terms, right? And hopefully by the maximum principle, then we are able to conclude that there's some rigidity happening. And to make a long story short, one of the main problems we have is that N is not abelian. Now this can be fixed by, it's a long story, so I will avoid this. But the other main problem is that for us, this function f, right, log square root determinant. Now this is the volume density of the n orbits, and this function is not going to be G invariant. Remember, we have this quotient. Now this is the one we are studying for the theorem, but this is the one that's compact. So I need to cook up G invariant functions so that I can use compactness of this base and apply maximum principle. If it's not G invariant, then there's no maximum principle, right? I mean, I'm not gonna be able to conclude anything from this. And the way we argue is so remember that the mean curvature vector is minus the gradient of this function, right? somehow this is not the right function because it's not G invariant for us. But instead of looking at that, we try to write the mean curvature vector as the logarithm of some function v plus some error, right? And now if you ask that this decomposition is a natural, gradient plus divergence free, then you're gonna be forced to having v equals to this thing, right? By uniqueness of that decomposition. So somehow this is not going to be divergence free. What we specify is that the divergence, a weighted divergence of the error is 0. But the weight also appears in the potential there, right? So it's like kind of a, it's not entirely clear why you can write that. In fact, V solves a PDE on the base, which is the following. So it's a divergence of Laplacian B plus V times some vector field equal to 0. So it's a linear PDE, right? And of course, the key point is that you need positive solution to this PDE, because then you want to take, I mean, this should be a volume density, right? And when we reach this point, I mean, we didn't know what to do because there's nothing in the literature that tells you this PDE has a positive solution, unfortunately, because there's a first order term and then there's a Schrödinger type term, zero order term. And now the fact that the L star, the dual operator, satisfies a maximum principle ensures that that there is a unique solution to this equation up to scaling, and it doesn't change sign, pretty much in the same way as you have it for the Poisson equation, right? The Laplace equation, sorry. And so with this V, we end up hooking up our function, which is in the same spirit of Tian, Neighbor, Lot, and Wrongs, but then it has some modifications due to the issues that I mentioned above, and we get the differential inequality. And then when rigidity, from rigidity, we can conclude that A vanishes, and that's the first step. Once you have that, then you need to play the game again with looking at the scalar curvature of the orbits. Also satisfies a nice PDE with the Laplacian of scalar curvature, and that gives you the Ricci solitons, and then you are done. So I wanted to mention a few open questions that we have in this setting. I don't know if I have time. I'm not sure. If I have 5 minutes, I do very quickly.
Absolutely, yes.
So the first question is, well, in the context of the Einstein equations under, on a principal bundle, we actually conjecture that, no, that I should not say this because we haven't written this on the paper, but I conjecture that, yeah, I don't want to attribute this to Christoph because maybe this is too ambitious. We haven't thought about this too much, but so let M satisfy negative Einstein equation, G invariant with compact orbit space. Now I'm not assuming that G acts freely, that the orbit space is a manifold. The orbit space is a compact metric space. Okay. Now the conjecture is that, and well, of course, the action is by isometries, right? That's natural. Then M splits isometrically as a product of G invariant homogeneous space So this is a homogeneous Einstein. And this is a, well, a compact Einstein manifold. So at the end of the day, the quotient is a smooth manifold, and the quotient is actually Einstein, and there's an isometric splitting, the orbits times the base. Okay. So this might sound maybe too ambitious, right? Only the fact that you have a group action with a compact orbit space forces a splitting, namely all the invariants in O'Neill's formulas vanish. The A vanishes and the T vanishes. And then the base is Einstein, and the, well, once the A and the T vanish, then you are done. Now we know this is true, and we are writing this up when G is semi-simple. Now this is very recent work, still not on the archive, but there's a splitting somehow. If you look at the Einstein equation with symmetry, with co-compact symmetry, then it splits as a homogeneous Einstein, which has no topology, times a compact Einstein manifold. This is what should happen at the end of the day. And maybe in the last minute, let me advertise this problem, which I really like, conjecture 2. This should be thought as the dynamical Alexievsky conjecture. So if you have a simply connected homogeneous space, G mod H, which is not diffeomorphic to a Euclidean space, right? So then the Alexievsky conjecture said, well, then it cannot have an Einstein manifold. Okay, so negative Einstein manifolds are Ricci flow solutions which have no singularity in finite time. Okay, now the claim is that then this should happen for any Ricci flow solution. So any G invariant Ricci flow solution on G mod H must have a finite time singularity. Okay, so not only you don't have Einstein metrics of negative Einstein constant, you don't have any immortal Ricci flow solution. The fact that there's some topology should force any homogeneous Ricci flow to end in finite time. And I hope that the methods that we are developing maybe help considering this problem, but this is we are very far away from a counterexample or from a solution. So let me end with this. Thank you.
Are there any questions or comments? Well, sorry, Claude, I still 1 second. In theorem B, which was the role of taking the nil radical?
Well, if you take G, we cannot prove it. So, I mean, there's this conjecture that it should hold for G and much more should hold, but we cannot show, for instance, that. So the first item is the A tensor vanishes, right? Mm-hmm. We cannot prove that for the G action. We can only prove that for the N action. It's less, right? I mean, it's if you think about it, it's a bit less. You ask me why? Well, I don't know. It's just you don't get it.
Another curiosity before I pass to Claude. In this conjecture, so I expose my ignorance, but there is no way to create singular quotients. I mean, so it's part of the conjecture that everything will stay smooth, whatever you do.
Yeah. Somehow, when you apply the maximum, I mean, you can still do, the maximum principle locally if the function that you cook up goes, say, to plus infinity at the boundary. If you look, I mean, if this is not a manifold, but there's an open dense set where this is a manifold. Okay. It can have a stratified set of singularities, very bad, right? But maybe on the regular part, you can cook up a nice function that goes to -infinity on the boundary, and then you apply the maximum principle there, you conclude it's constant. So then there is no singular part. Yeah,
But,
I don't know if it makes sense.
This substatement is known. I mean,
No.
Even just the fact that you can create singularities by playing this.
Yes, you don't create singular. I mean, you somehow avoid singularities. Like you conclude that the quotient is smooth at the end of the day. Yes. No, but this is what happens, for instance, in the work of Neighbor and Tian, that they don't assume that they don't have that the action is free, but it follows at the end of the day because of what I said. I mean, this essentially this density, you can define it on lower dimensional orbits. So that the singularities of this quotient are due to some orbits having less dimension than the typical orbits. Imagine the sphere, right, with a rotation action. So what's the quotient here? It's an interval, right? It's not a smooth manifold. Yes. So the problem is that these orbits are too small, right? But somehow the volume density can be extended everywhere, but the logarithm of 0 and -infinity, you know, so then still, if you have the right sign, the maximum principle works, and yeah, no worries.
Could you say more about the role of the Ricci-Solomon structure of these n orbits?
Yeah, this is actually perhaps 70% of the paper to deal with that, but unfortunately I couldn't. I mean, it turns out that the fact that n is non-abelian makes the orbits have curvature. And this, if you look at O'Neill's equations, is very bad because there are terms appearing with the wrong sign. You don't want the n orbits to have curvature if you want to play these maximum principle arguments. By the way, I should have said these papers are not about, they don't say we solve this equation, right? But to me, the core part of the argument is about looking at the Einstein equation with symmetries, and this is how they deal with it. So I just want to emphasize that I'm not claiming, you know, we generalize all these papers. No, please no. But yeah, the fact that there's curvature of the n orbits, you need to introduce a weighted version of the volume density. And the weighted version is going to be something like, suppose Gij is 0. So suppose the metric is diagonal in your frame. You cannot assume that, but there's a way around it. Then you can define a new volume density by saying you look at the product of the eigenvalues raised to a certain power. And these are different powers. And somehow these numbers, you take these numbers from geometric invariant theory applied to the action on the space of, on the vector space of all the algebra laws. And this is a really long story, but they were known to be related to the geometry of invariant metrics on these groups. So somehow we use this to study the immortal homogeneous Ricci flow with Christoph, and somehow looking at this weighted volume density where the weights come from GITs, there's a lot going on related to the work of Francis Kirwan in the 80s. But this is what you need to do, and somehow with this, well, you get a nice PDE. This somehow takes care of the curvature of the n orbits. And yes, yeah. The curvature estimates have solitons. They are sharp on solitons, so that's why at the end of the day you get the soliton equation on n.
Any other question, or it won't tell you the vector field? So,
so concerning still concerning soliton. No, sorry. Concerning the Aristotelian conjecture, I mean, what is known or what do you expect if you just assume that your manifold is a soliton?
No, same statement. Yeah, it follows pretty immediately. Yes. Okay. I mean, not immediately, but this same statement is true for solitons. Yes.
And it's trivial. I mean, from your proof. I mean, or?
Yes. From knowing the Alexiesi conjecture. Yes.
Okay, it was known. Okay.
It was. They were known to be equivalent. This is not trivial, but
okay.
But it was known. Yes.
Okay.
I did this in my PhD thesis.
Okay.
Yes.
Thank you.
Yeah. No worries. Good question.
Well, okay, so we thank Ramiro again.
Thank you.
Okay, so welcome back, and very happy to introduce you Anna Dall'Acqua from Ulm University, and she's talking to us on some results on the Willmore flow.
Thank you very much for the introduction. Thank you very much to the organizer, Giovanni and Andrea, for the kind invitation to give a presentation here. It's a great honor for me. The title says some results on the Willmore flow. So actually I will mostly present one result, and I hope at the end to make a bit of publicity to some result of Fabian that is also here at the conference. So that's why the plural on the title. Tristan spoke already about Willmore. So let me introduce my notation, my situation. So here sigma denotes a two-dimensional compact manifold without boundary. So that's very general, but actually most of the talk sigma is or the two-sphere or a torus. And we consider F an immersion from sigma to R3, are smooth immersion, sufficiently smooth. And for such F, we define the Willmore energy. So for me, we go to R3. Tristan were in S3. I consider the Willmore energy to R3 as the integral over sigma of the mean curvature square with respect to the induced area measure. So H here is the mean curvature vector, and mu is the area measure induced by our immersion F. So this energy, all of you know it, but well, it's interesting from a geometrical point of view, and it comes from application in elasticity, which are the most important feature about this energy. It is invariant with respect to conformal transformation R3. So if phi goes from R3 to R3, a conformal transformation that is smooth on F of sigma, then the Willmore energy of phi of F is the same as the Willmore of energy of F. So it's invariant under conformal transformation of the ambient space. We need that when we take an inversion, that is the point is not on the image. So in order to have this conformal transformation. What Willmore already observed, but this goes back before him, is that the Willmore energy is always bigger or equal to 4 pi in this situation with equality if and only if sigma is the sphere and F the round sphere, so an immersion of the round sphere. Very important question was minimization about this functional among surfaces of fixed genus, and this has been established by Simon, Leon Simon, and then also with the contribution of Bauer and Culvert. So we know that we have existence minimizer for any fixed genus. Critical point of this energy are called, so I forgot to write the name, but probably all of you know it, but for completeness, let's write it. Critical point are called Willmore surfaces, and Tristan Riviere proved that every Willmore critical point, so every Willmore surface is real analytic, so they are smooth. So Leon, Simon, Bauer, Kubert, we have the existence of minimizer for fixed genus, and what today will play a special role is the case p equal to 1. The case when we have 1, so genus 1 case, so P is here, the genus, and we know that the minimizer is attained by the Clifford torus. That was the famous Willmore conjecture proven by Neves and Marquez what Tristan also presented today. And this energy is 2p squared. So that's the case for the Willmore flow, this energy. What we want to speak about today is the Willmore flow. So we want to take the gradient flow with respect to this energy. So what is the Willmore flow? Sorry, I should look at my note. Another important thing is that we have for the Willmore energy is the Li-Yau inequality that also plays an important role, that tells us that if we have an immersion with Willmore energy strictly smaller than 8 pi, then F is an embedding. So that we will know. So please note that the very important number 8 pi here for the Willmore energy. What I would like to study today, to look with you, is the L2 gradient flow associated to this energy, that is the so-called Willmore flow. So it's too important to write it below there. So let's go here. We look at a family of immersion moving with respect to time in the direction of the L2 gradient of the Willmore energy, that we can write as minus the Laplace of the mean curvature vector plus the square of the trace-free part of the second fundamental form times the mean curvature. So we are looking at a family of immersion moving in the steepest descent direction of this energy, started with some initial D2. So this has been studied a lot in the literature with many contributions, started from, I will say, so the first I aware of is from 2001 by Simonette, that considered the Willmore flow with initial data F0 that are C2 alpha near to the sphere. And he proved long-time existence and converges to the sphere when we start C2 alpha near to the sphere. So in this case, sigma is the sphere, and we are at C2 alpha near to the sphere. Then there are many works by Kubert and Schätzle starting in 2001 and continuing to, I would say, what did I say, up to 2004 by Kubert and Schätzle, where they study the Willmore flow first for general sigma, and at the end, the result, the most general result that they have, it says that if the initial datum is smaller than 8 pi and sigma is the sphere, then the Willmore flow is global, so there exists a solution for all times that converges to the sphere. Then another contribution that is important is in 2009 by Gilles, Fasankova, and Schätzle. What did they do? Schätzle. They studied the Simon-Loyasiewicz inequality. That's a very important inequality for our energy, such that when we have this inequality, we know something about the behavior of the flow when we are sufficiently near to critical point. And the result of one of the results of this paper, studying the Loyasiewicz inequality, is what they can prove is that Willmore blow up are never compact. So blowing up, so looking Willmore flow, we blow up, then what we know that what comes out cannot be compact. Right, and then in the last year, there is also, so there are many contributions, and one of the recent one, 2020, Palmurella and Riviere, Murella, Palmurella. No. Yeah, they propose a parametrization, so a new approach to the Willmore flow using a parametric approach. So on the other side, we have, so here the result of Simonette and Kubert and Schätzle give us global existence when we have energy below 8 pi, and in the case of the sphere, what happens above 8 pi. So here there are some results by first numeric, by Meyer and Simonette, and then analytically by Blatt, that shows that there are initial datum just above 8 pi for which the flow will develop a singularity. So there exists initial data F0 from the sphere to R3 with energy arbitrarily near to 8 pi. So you give me an epsilon, so you give Simon Blatt, Maya Simonette an epsilon, and I can produce an initial datum with energy just above 8 pi, such that the flow develop a singularity. And how does it look like, this initial datum? The idea is that one looks like that. So here is a piece of a sphere. Here we have a catenoidal neck, catenoid neck, and then here again a sphere, and you should think a surface of revolution, so that we have here a closed curve with winding number 3. And what we expect is that with the flow downward, this catenoidal neck will disappear and go through in the direction of this axis, so converge to the two sphere. But then the winding number of the curve is going to change, and then there has to appear singularity on the flow. And as you see, so far, most of the results are in the case of the sphere. And then, so the question, or what I wanted to present to you today, is a contribution in the case of tori. So we want to look now at the case of tori. So sigma is S1 times S1. But in order to be able to do something, we need to add something. We had a symmetry. So we look at tori of revolution. And in the case of tori of revolution, I will write our result later on the blackboard. Our result is very similar to the one of Kubert of Schätzle, that if we have an initial datum with energy below 8 pi, then the Willmore flows converges, so exists for all times and converges to the Clifford torus. But we have to look at tori of revolution. So what we are thinking of is we have here some curve, and then we rotate it around the axis. So in this special situation, we want to prove the same result as Kubert and Schätzle. Before starting giving you the result and our step, the one step of the proof, I would like to give a motivation how we come to the idea that we can study this situation. And this is connected with some work I've been doing in the last year, and connected with an idea that goes back some long time ago by Bryant and Griffiths and Pinkel. And they noticed that there is a very nice relationship between the Willmore energy of surfaces of revolution and an energy on curves. So which is this relationship? So we consider now gamma a curve in the hyperbolic half space. So we are looking now at the hyperbolic half space here with the hyperbolic metric. And we look then at the immersion obtained rotating this curve, so at the torus. So what is the Willmore energy is the mean curvature square. So what we are looking at the two principal curvature of given by these immersions. And we are looking at the surface of revolution. So the curvature that we have on one side is the curvature of the curve, and the other is the curvature due to the rotation. And of course, the rotation, the curvature is highest when the curve is nearer to the x-axis. So the smaller this distance, the curvature of rotation will be bigger. And that's exactly how it works also the hyperbolic metric. So it becomes singular when we approach the x-axis, and that is an intuition for the following the relationship, the fact that the Willmore energy of the surface of a revolution induced by the curve gamma is equal to p½ the elastic energy of gamma, where the elastic energy is nothing else that's 1/2 the integral of the curvature squared with respect to the arc length. So there is simply a constant computed the elastic energy of the curve with respect to the hyperbolic metric. So we take simply the curvature of the curve we take a square, we integrate it, that is multiplied by p-half, exactly the Willmore energy of the immersion. And this relation we have been using in the last year a lot to study Willmore surfaces of revolution. No, alles gut, thank you. Not yet. Okay, so this relation we had, and why did we got the idea that we can do something for tori of revolution? So with the former PhD of mine, Adrian Spena, we looked at the Willmore flow, at the elastic flow on the hyperbolic plane. So we look at the elastic flow for this energy. So we look at curve developing with respect to the L2 gradient of this energy. And we were interested in long time existence. That's exactly not the energy we looked at. In order to be able to prove some existence, we penalize the energy with the length of the curve. So it turned out, in order to show for this flow, so with some initial datum, and now here we are in the hyperbolic space, half space. In order to be able to prove global time existence for this flow and converges or subconverges, we needed to penalize the elastic energy with a length. So here there is this parameter lambda that is strictly positive. So we looked at this flow of curves in the hyperbolic plane, and we show that whenever lambda is positive, the flow exists for all times, and it subconverges to some critical point of this energy. And then we ask ourselves, do we really need this lambda? So I didn't know, but then Adrian and Marius Müller, they proved a new inequality, a very nice one that we have been able to show that if the elastic energy of the curve is smaller than 16, then the bound on the elastic energy implies a bound on the hyperbolic length of the curve. Okay, and then you say, yeah, and what? Then look at this number. This number is 16. Elastic energy is smaller than 16. What does it tell us for the associated surface of revolution? Tells us that the associated surface of revolution need to be Willmore energy less than 8 pi. So then comes again the 8 pi of Kubert and Schätzle, and right, if I can avoid the lambda here, so there is no need here for the lambda, then it looks like we are very near to the Willmore flow with this flow. That's not the same flow. Because we are taking the, we have different metric with respect to which we take the L2 gradient flow, but it is inequality indicates, okay, perhaps here we have something that we can use to try to control, to understand something about the Willmore flow of tori of revolution. And this indication turned out to work. And that's the main result that I got together with my co-author, very joint work with Marius Müller, former PhD in Ulm that now is in Freiburg, Rainer Schätzle, and Adrian Spena. So what can we prove? So let F0 be a torus of revolution. So we have our initial datum that is a torus of revolution, and f of t for t in some interval with the maximal Willmore flow with this initial datum. Okay, The first is that Kubert-Schätzle already says the Willmore flow in general case is a well-posed problem, so there is short-time existence and uniqueness. And from the uniqueness result, we can follow that for each time the flow remains rotationally symmetric. That means that for each time I can associate to this immersion a curve. So let gamma t be the profile curves associated to this tori. Okay, then the main, so if the length of these curves, the limits inferior, so the limits inferior of this of the length of these profile curves for t going to the maximal existence time is finite, then the flow is global and the flow converges to a Willmore immersion, a Willmore torus of revolution. Willmore torus of revolution. So we found out which is the quantity that we need to control in order to have global existence and convergence to a Willmore torus, and that is the control of the hyperbolic length of the profile curves. Thanks to the inequality of Marius and Adria, we can say if the initial datum has energy below 8 pi, then we know that the length is controlled. And then in this case, we converge, we are global, the flow is global, we converge. And in that case, we can say which is the limit, and the limit is the Clifford torus. So. Grazie.
So we're starting with something which is a force of revolution, but presumably not
I could, right? Then it's a bit yeah. Not interesting, right? It keeps being the Clifford torus since a critical point. Yeah.
So I was just wondering about the. Could you explain the role of the penalty of
here? That plays no role in our theorem. That was earlier motivation where we started from. So we first studied this flow, and then we noticed that for our analysis in the hyperbolic half plane, we needed a penalization of the length in our in several points in the arguments. But the question was, why do we need it? And so that's why Adrian and Marius, they studied if some bound on the elastic energy implies a bound on the length, and they found this threshold of 16 for the elastic energy. And then, 16 is 8 pi, ho, ho, ho. And that was the motivation for looking at this situation. Yeah. So in fact, the elastic flow doesn't play a role here. So it seems that I wrote too strong. So the blackboard. Okay. So, so if the Willmore energy of the initial datum is smaller or equal than 8 pi, then the elastic energy is bounded. And Ft converges to the Clifford torus. Okay, so that is for the global existence part of the flow. We had, of course, in mind the example of Meyer and Simonet of Blatt with this disappearing of a singularity, and we can do it also in our case. Moreover, for all epsilon positive, we find initial datum with Willmore energy above 8 pi and smaller than 8 pi plus epsilon, such that the Willmore flow does not converge. What does it mean? What happens? Either there is concentration in the sense that the norm of the second fundamental form becomes unbounded, for t going to the maximal time, or the diameter of our immersion becomes unbounded. Yeah, so that's our main result, and actually most of the work have been already done in the works that I told you before, the one by Kubert and Schätzle and Gilles Pazankova and Schätzle. So here I write down a result that we wrote down in the paper, but it's putting together, I will say, the state of the art for this approach to the Willmore flow. That tells us the following. In the case of the torus, we look at the so-called curvature concentration function that is defined as follows for t between 0 and t and some radius positive. What we do is we look at the integral of the pre-image through our immersion of the ball of radius r centered first at some point x of the second fundamental form. And we take the supremum of that in any point in R3, and that gives us a function that depends on the time and of the radius. That was looked at by Kubert and Schätzle, and they proved indeed then that there exists epsilon 0 positive, and there exists a constant positive, such that if we look at time going to our maximal existent time, and if we call Rj the supremum of the R positive, such that this curvature concentration function at time Tj and R at R is less or equal than this epsilon 0 threshold. So there exists a threshold for the curvature such that when we take times going to the maximal existent time, we take the radii such that the supremum of the radii such that the concentration at any point of R3 is smaller or equal than epsilon 0, then what do Kubert and Schätzle says? They said, okay, then the flow exists also at time Tj plus C Rj to the 4. That's, of course, the parabolic scaling. We have a fourth order equation. So Kubert and Schätzle says, okay, at time Tj, we can move of this constant Rj to the 4, and that is still smaller than the maximal existence time. So at that time, the flow will still exist. Moreover, what we do now, we look at that time and we look exactly, so with rescale with the radii Rj's, we look at f tilde jc, that is f at time Tj plus C Rj to the 4 divided by Rj. So we look at the time a bit farther than Tj and we rescale with this radius Rj. Then, so far we didn't say anything about this radii. And then we can say if the radii remains bounded, so there is no blow up, no blow down, then the time, the flow is global. I mean, that is clear because we are adding a fixed constant, a bounded constant, so can be infinitely many times, so we reach everywhere. Okay, so that's that. And if the diameter of this rescaling is bounded, then the rescaling converges to a Willmore immersion. And in this special case, then we can also say, since the diameter remains bounded and it's proper the immersion, we can identify again. So we are again a torus at the limit. Okay, so this is what is based on this result. This can be found by Kubert and Schätzle together with the result of Chilfa, Zankova, and Schätzle that says that Willmore blow-up are never compact, so that when if the diameter is bounded, then we must converge to something. So that was something that is the state of the art. And this is where we started and looked, so what can we use here? And now if you compare our result with this main tool, where is the difference? Here, applying the theory of Kubert and Schätzle and the Loyazievich inequality, as criterion we have that we need to control the diameter. In our statement, we say we need to control the hyperbolic length. And now the question is, are the two things related? So if I can control the hyperbolic length, can I control the diameter? And you can think a second about that while I clean the blackboard. Yes. Yes. Thanks to Marius, and I tell you in a second why. So where were we left? So in our our theorem that now unfortunately is half gone, but the main condition that we have is that we need that the hyperbolic length remains bounded, whereas using the theory developed by Kubert and Schätzle together with the Loyazievich inequality, we need a control in the diameter. So is enough to control the hyperbolic length to control the diameter? No, because if you take some curve in the hyperbolic plane and you move it upwards, the hyperbolic length will decrease, but the diameter of the surface of revolution that you create will increase, right? So the diameter is simply the diameter in R3. So that moving this curve upwards, the diameter will become unbounded. So bounded the length, the hyperbolic length doesn't give us a control of the diameter. So, but not directly, we need something more. So what we need is a control of the radius of revolution. So I need a control that tells us that along the flow, the profile curves doesn't tend to go up. So I want to control this distance to the axis, so what we call the radius of revolution, to be sure that the control of the hyperbolic length it has also a control on the diameter. So, all right, so need a control on the radius of revolution. So you agree. I mean, I take this curve, I move it upwards in the hyperbolic half plane, its length will decrease because so the second coordinate of the curve will decrease, right? But then if I look at the surface of revolution, moving the curve up, then the diameter will really increase. So how to control the radius of revolution? And then again, we look at the concentration function we have there. So we fix now bed point. So what is a bed point? A bed point is where the second fundamental form concentrates. So let's say that a bed point is a point. So we take a ball of radius rj at the point xj, such that the integral of this ball of the second fundamental form is at least epsilon 0, right? So we look at points. So I'm thinking always of taking the rotation, and I take a point here, such that in this ball of radius rj at the point xj, so that's the point xj, that's the radius J. Here, there is some concentration of the curvature. Okay, now we do a rescaling in order to be able to get, instead here of radius Rj, we look at the radius 1. So we look now at f of Pj, Rj. So making this rescale, we get here a 1. Of course, we are using the conform invariance of energy, so we can work with rescaling. And then here we get still a contribution of at least epsilon 0. But then we have here a radius 1. So now during the rescaling, this radius here, so now we don't have anymore the point xj, but here we have now Fj divided by Rj, but now the ball of radius 1 contributes to epsilon 0 to the curvature. And each of these ball contributes with an epsilon 0. And what are we considering now? We are considering a surface of revolution. So every time we have a bad point, Mario says, and the thing is we have also a bad circle, right? Because of the symmetry that we are considering. So that the circle that I get when I rotate the curve, each of the ball will also have this concentration of epsilon 0. So when this distance here become very big, I have space to put a lot of ball of radius 1. But then due to the bound on the Willmore energy, then I cannot, this radius of revolution cannot become too big. Otherwise, there is space for too many ball of radius 1, and then we will get above the energy of the initial D2. So with this observation, we get a control of the radius of revolution. So we have not only a bad point, but due to the revolution symmetry, we get also a bad circle, and that is too much with the for the energy. So the radius, so with this observation, the radius of revolution is bounded. So the curve along the flow cannot escape to infinity in the upward direction. And then when we can control the hyperbolic length, then we can control also the diameter of the surface of revolution. If the diameter is bounded, then the theory of Couvert and Schätzer, that is based on the theorem of Langer, tells us that we converge to a Willmore immersion. The radius of revolution is bounded, then if then the diameter remains bounded. And then we have converges to at F infinity, that is a Willmore immersion. Okay. So far we didn't use the assumption of 8 pi. So far we only use the assumption that the hyperbolic length remains bounded. So when the hyperbolic length remains bounded, the diameter remains bounded, and then the theory based on the interpolation and concentration result by Couvert and Schätzer tells us that we have converges to a Willmore immersion that is also again a torus. Now, if our initial datum at energy smaller or equal than 8 pi, so let's make it first strictly smaller than 8 pi, then if the Willmore, so the initial datum at energy strictly smaller than 8 pi, then the inequality of, sorry, now it's gone, of Marius, so of Müller and Spener gives us that the hyperbolic length is bounded, and then we can apply the result and we converge to a Willmore immersion. Why it has to be the Clifford torus, so then we converge. So the flow is global first, and we converge to F infinity plus converges to a Willmore immersion. Okay, and now the analogy to the hyperbolic plane plays again a role, due to the fact that along the flow we are always tori of revolution, that the limit is again a torus of revolution. So I know that there is a Willmore immersion and it's a torus of revolution. That means that the curve, the profile curve, has to be an elastica, because due to this relation between the Willmore energy and elastic energy, if we have a critical point for the Willmore energy that is a surface of revolution, then the profile curve is a critical point for the elastic functional. And luckily for critical point of the elastic function, there is a classification due to Langer and Singer. And starting from that classification with a lot of work, Marius, Müller and Adrian studied the possible closed elastica, and they are able to show that there is no other closed elastica with energy below 8 pi other than the Clifford torus. And that's why, so thanks to the classification of elastica, we get that the limit is the Clifford torus. So let me say that for this convergence result, I mean, classification results are basic, are not basic, are fundamental. So by Kubert and Schätzle, they really needed a classification result of Brian for Willmore surfaces. Here, working with surfaces of revolution, we can base our theory on the classification of elastica. Okay, what happens with initial energy 8 pi? There is no Willmore surfaces with energy exactly 8 pi that is a surface of revolution. That comes again through the classification of elastica. So if we start with an initial datum that has energy exactly 8 pi, since it is not a critical point, the energy will immediately go a bit down. And when we are a bit down, then we can apply the theory we had before. And so we can start, okay, we can allow also for 8 pi. Which gap? So there are elasticas. There are elastica that so there are a lot of elastica, right? Can you? What do you mean with your answer? We can with elastica. So this I don't know. No, I don't know. I don't know. I don't know. Yeah, I don't know. So for yeah. Or I should look it up. So I don't know here in the spot. Could be that in the work of so the classification of elastica of Langer and Singer. So they give they solve the elastica equation in terms of a Jacobi elliptic function, and then Marius has to study, Marius and Adria, so Müller and Spena, had to study very carefully the conditions such that they close up. Because if you solve the elastica equation is an equation, well, all in terms of the curvature, then you get a formula for the curvature, and we want to get back to the curve. So one has to play with the parameter of this classification in order to see when you close up, and then try to compute the energy. And we have some understanding, so for what we needed here, but everything more I will need to look it up. Sorry? So below 8 pi, right? Smaller or equal than 8 pi. So we're thinking the hyperbolic, there is the one generating the Clifford torus. There is only that one. Yeah. So now I have, so there are, so the picture by Langer and Singer, they are always with the Poincaré half plane. So they have, there are these, how do they look like? Oh yeah, there are those, I'm not sure, there are the one with 3 or 4. So actually Manuel knows, so perhaps let's, so there are these wave-like and there are the orbit-like and there are, so there is a zoo of them. So I cannot pretend I have an understanding. So Marius studied really carefully to look. Embedded. Yeah, I think so. The other have all steps. I would think so. Yeah. Embedded, sorry, yes, yeah. The one really giving rise to the Clifford torus. Yeah, you're right. And also in Rn, yeah. Okay, so what I wanted to talk you about also this optimality result, this singular example. So we claim that for every epsilon positive, we can find an initial datum just below 8 pi plus epsilon and above 8 pi. Where the Willmore flow does not converge. So we don't know if the existence time is finite or infinite. That's an open problem. Also in the case of sphere, also in the example of Blatt. And again, what we do is we can find some initial datum F0 that looks like figure 8. And what are the property of this curve? They have Wandin number 0, and the Wandin number is an invariant along the flow, so that will kept along the flow, and there is no elastica. So we start with such a curve, and there is no elastica with energy around 8 pi or below 8 pi plus epsilon. And hence the Willmore flow cannot be global because cannot converge, because otherwise it will convert to such an elastica. So the idea is to start from such a kind of figure 8, and we can construct such figure 8 with energy arbitrarily near to 8 pi. So starting from such initial datum, the Willmore flow will not be able to converge. So either there is concentration of curvature or the diameter will become unbounded. Okay, so these are this is the result I wanted to present you about Willmore tori of revolution. So perhaps in the last 5 minutes, I would like to tell you also some result that came from the our group, so from Fabian actually. So which are here the ingredient that in my opinion has been fundamental, so have been used. On one hand, we have the Lojaziewicz-Simon inequality. And then this concentration technique based on interpolation inequality developed for the Willmore flow by Kuvert and Schätzle. And the question that we found interesting is how much of that can be extended also when we have some constraint along the flow. And so the question is, so look at the Willmore flow with constraint. And there are several results in the literature, and also specifically prescribed in the area or prescribed in the volume. So Fabian Rupp last year studied the Willmore flow under an isoperimetric constraint that make, of course, sense since the Willmore energy is invariant under conformal transformation. So we want to fix something that due scaling with scaling does not change. So, and then he looked at the isoperimetric ratio. So Willmore flow. Under fixed isoperimetric ratio. So what you look at is that this quantity kept it fixed along the flow, and that is of course okay between 0 and 1. So here we are in the case of the sphere. By 1 is not so interesting because it's only the sphere, so we look just below. And what one needs to study this flow is the inequalities developed based on the concentration on the second fundamental form, concentration of curvature, and the Loyazievich-Salmon inequality. So here Fabian proved, so has a nice result where he proved the Loyazievich, so proof under which condition an energy functional with a constraint satisfy a Loyazievich-Salmon inequality. That's a very quite general paper on which then you can take and look if you can apply the result. And then he was able to extend this technique by Kubert and Schätzle, allowing for Lagrange multiplier that in this case with the fixed isoperimetric ratio were quite involved. And yeah, and so Fabian was able to prove, did I write it here, the final result? Yeah. So if the initial energy, the initial datum has energy below 4 pi divided by sigma and 8 pi, then the Willmore flow for, in the case of the sphere, exists for all time. It keeps this isoperimetric ratio fixed along the flow, is global and converges to the sphere. So right, and yeah, that's what I wanted to tell you. Thank you.
Are there any questions?
What about the conformal class of the underlying Riemann surface? So how does it behave in these finite time blowups? So I guess they are still bounded, or?
We don't, so we didn't study yet here what exactly happens. We expect that this part will disappear and go down. And
yeah,
probably
but in the moduli space, so is it going to infinity or is it controlled? I guess
going
it's
down. I think it's going down to the axis of revolution.
Yeah, but the conformal class is not the geometry,
yeah,
the
okay.
underlying Riemann surface. So because there is an issue about, you know, so is a Willmore flow, does it blow up in finite? Can it be that the conformal class blow up in finite time? So in your example, I guess the conformal class is, when I see it, is controlled, no?
I didn't think about that, so I have to. Yes, yeah.
Yeah, but yeah, it will be a rectangle, but it can be very thin. But I think it's not the case. I think the size of the rectangle is controlled. My impression, but maybe I'm wrong.
Interesting. We can speak about that. So as a byproduct of the result, we proved that there are, for each conformal class, there are torus of revolution, because if we, yeah, that's a byproduct of this Willmore flow approach.
Okay, thank you.
Then, yeah.
Thanks.
Suppose you start with an immersion of the circle in the hyperbolic plane, which is not an embedding, but let's say it has positive curvature. It has curvature of fixed sign. Is it plausible that perhaps the flow always moves that to a multiple cover of a Clifford torus? In other words, if you assume that you have a sign of the curvature of the curve, if it's locally convex, is that property preserved along the flow? does it tend to push it to a, so it might maybe push to a circle?
A multiple cover of the Clifford torus. This, I don't know.
This is just a wild guess. I don't know anything about the subject. So.
I mean, there are of course the technique based on the Lojasevic inequality that tells you, since you have the Lojasevic inequality, if you start in a neighborhood of your critical point, then it will converge to that. So sufficiently near to that, it will work. More than that, we cannot attack. Thank you.
So I wanted to ask, if I'm not mistaken, when you wrote the example where blow up occurs eventually, so you wrote that the L infinity of the second fundamental form blows up. So in principle, you would expect that, so at a singularity, the L2 norm of the second fundamental form has to blow up, no? NT. So this is, I think, what also Kuber. How comes that you couldn't get from L infinity to L2? Because the technique, I think, rely on.
Could be that was a typo, you know.
I mean, I thought about it and I said L infinity, which is strange. It will be L2 because L2 Wettenschatzler.
That's the same result as in the application of Kubert and Schätzle. So that's yeah. So I apologize for that.
Sorry, I have another question.
Thank you.
There is another class of equivariant tori, which is particularly interesting, according to me, to study as well, which is the class of Hopf tori. That is, you look via the Hopf map at the pre-images of curves on the two spheres, and then you run the flow.
Okay.
So, because there you can visualize the conformal class easily, thanks to a result by Pincal. You know, it's the vector is going to be given by the area and the length, the enclosed area and the length. So I was wondering if your approach could be also considered. I don't know if it can be reduced to some elastica or something. Can be so if your approach is yes, could be looked at, could be transposed in this class of Hopf tori.
Okay. I have to look at it. It will be happy because it's. I mean, it will be wonderful. I mean, that's the strength. So we had luck that this understanding. So thanks to this inequality of Marius and the other, but so behind this inequality, there is really a lot hard work study the classification of the elastica. So I will say that the moral is if there is some geometry that I can simplify to which I can, at the end, I get a classification to something that is no, then you get something out of it, right? For the Willmore flow, at the end, you need some classification, some understanding of the critical point. So if that is also there, then that will be wonderful to look at that. Thank you. Thank you. So, yeah.
But it would be more complicated than a torus of revolution if you try to decompose it from hyperbolic cross arc, no?
I think there's even an expression of the Hopf energy. There is, if I remember well, the paper of Pincal, there is an expression of the Hopf energy in terms of the elastica on S2.
Okay.
Something, but maybe with some terms I forgot. And then maybe this approach, it would be very interesting to look at the maybe the differences or the similarities in this equivariant class. Yeah.
Thank you.
Yeah, the Clifford torus is the equator. Then you have all the CMC Clifford tori, but which have more and more infinite energy, Willmore energy. But it's also, yeah,
It should be also
What
interesting.
one will then one will need some control of the concentration, right? This step from the bad point to the bad circle. That we will
Yeah,
need
but you
to
should see it on the curve on S2. You should see, you know, the L infinity norm of A going to infinity should correspond to a point where the curve is really turning very fast. Similarities.
Okay.
Yeah.
Thank you.
Any other question?
I missed a few minutes, sorry, but I saw that picture of the non-embedded sphere. What does the numeric say about that?
About the time? Or no?
Yeah, does it expand or?
The example of blood,
Yes.
that it will go to the two sphere. So the scatenoidal neck will shrink and go to the axis. So it will go to two spheres.
The diameter will stay bounded.
Yes.
Okay. Thank you.
Any other question? All right. In that case, we thank Anna again and see you tomorrow morning.